At the beginning of the 1990s, the global system for mobile communications triggered an unprecedented transformation in the way people communicated. Earlier analog wireless telephony systems, such as advanced mobile phone systems or Nordic mobile telephone, were limited in scope, being country-specific and used by only select few. These systems often suffered from poor interoperability and limited user capacity. In contrast, GSM, a global system for mobile communications, represented a global standard designed to facilitate compatibility across borders and cater to a far longer user base. By the late 1990s and early 2000s, GSM had been adopted worldwide and served billions of users during its peak, revolutionizing personal and business communications. This widespread adoption was largely driven by ongoing advancements in telecommunication technology, which led to significant cost reductions for both infrastructure equipment and mobile devices. Affordable devices paired with widespread network deployment made mobile communication accessible to the masses. GSM's architecture, with its scalability and adaptability, also laid the foundation for packet-switched extensions like General Packet Radio Service and enhanced data rates for GSM Evolution, which provided early mobile internet services. These systems are discussed in detail in next lectures, but moreover, GSM served as a precursor to more advanced technologies such as the Universal Mobile Telecommunications System, UMTS, and High-Speed Packet Access, HSPA, which are covered in next lectures. The journey of GSM began in the mid-1980s when the European Telecommunication Standards Institute, ETSI, initiated the standardization process. Despite its origins in this era, GSM remains in use today, demonstrating its robustness and adaptability. While its role has diminished with the rise of 4G LTE and ongoing deployment of 5G networks, GSM continues to play a crucial part in modern mobile communication systems, particularly in regions where advanced networks have not yet fully replaced older infrastructure. With the advent of 4G LTE networks, voice communications has evolved through the introduction of Voice over LTE. This service allows voice calls to be transmitted over the LTE radio network, providing superior call quality and faster connection times. However, the transition to VoLTE is still incomplete. Many devices, especially older models and some networks, lack VoLTE support. In such cases, mobile voice calls rely on flashback mechanisms reverting to GSM or UMTS networks for call handling. Additionally, the GSM and UMTS networks remain the backbone for voice telephony during international roaming. As of creating this course, only a few operators have extended their VoLTE services to support seamless roaming, leaving GSM and UMTS as critical components for global voice connectivity. Understanding GSM's architecture and evolution is vital for grasping how modern mobile networks function. Over the years, the deployment of GSM networks has undergone substantial changes. Initially, the GSM systems were designed with relatively simple structure aimed at providing basic voice services and SMS. The original architecture comprised a base station subsystem, BSS, for handling radio communications, a network switching subsystem for call routing, and operation and support subsystem, OSS, for network management. As user demands grew and the technology advanced, GSM evolved to support additional features such as GPRS for data transmission, Edge for higher speeds, and integration with IP-based services. Today, even as GSM coexists with more advanced networks, its legacy endures. It continues to be a critical fallback option, especially in rural or remote areas with limited LTE or 5G coverage. GSM's compatibility and reliability make it a valuable tool in scenarios like disaster recovery, machine-to-machine communication, and emergency services. In summary, GSM not only transformed mobile communication during its heyday, but also established the foundation for subsequent generations of wireless technology. Despite the dominance of 4G and emergence of 5G, GSM remains relevant in certain contexts, particularly for voice telephony and basic connectivity. A deep understanding of GSM's architecture, evolution, and practical applications is essential for anyone involved in the deployment and management for mobile networks today. This section will first explore the original design of GSM and then trace the significant enhancements that have shaped its evolution over the decades. Initially, GSM was designed as a circuit switch system, mirroring the structure and functionality of fixed-line telecommunication networks. In this design, a dedicated direct connection was established between two users for the entire duration of call. This connection spanned every interface between all network's nodes involved, ensuring an exclusive path for communication. While this approach guaranteed a reliable and uninterrupted link, it also meant that network resources were locked for duration of the call, even during periods of silence. Over time, advancements in technology and growing demand for more efficient communication methods led to the virtualization of physical circuit switching. Today, GSM networks nodes are typically connected through IP-based broadband connections, allowing for more flexible and efficient resource usage. And here in this lecture, you will also learn about the overview of the traditional architecture of circuit switch GSM networks, while later in this lecture, we will explore the transition to virtualized circuit switching and its benefits. The GSM mobile telecommunication network was initially modeled after circuit-switched fixed-line networks. These systems relied on establishing a direct and exclusive communication path between two parties, ensuring consistent voice quality and reliability. At the beginning of a call, the network would set up a connection between the caller and the receiver, and this path would remain dedicated to their conversation until the call ended. In this illustration, you can see the switching matrix employed in a traditional switching center. This matrix acted as the central component for routing calls, connecting the originating party to the destination party. Once a connection was established, the conversation flowed transparently through the matrix, with the switching center intervening only to clear the connection when the call concluded. And this circuit switch approach was not unique to mobile networks. Fixed-line telecommunication networks of the time also employed similar mechanisms. Initially, these networks transmitted analog signals directly between subscribers, creating a continuous electrical circuit. However, the mid-1980s saw a shift toward digital technology in switching centers, marking a significant improvement in how calls were processed. And in this new digital paradigm, analog voice signals from subscribers were digitized by the originating switching center. The digitized signals were transmitted to the terminating switching center. At the destination, the digital signals were either converted back to analog or processed digitally, depending on the type of subscriber equipment. In countries where integrated services digital network, ISDN lines were popular, the entire transmission process became fully digital. And ISDN allowed for better call quality and faster data transfer rates, as it eliminated the need for analog to digital conversion during transmissions. And the conversion to analog signals occurred directly in the user's phone, ensuring seamless communication. When GSM was standardized, it reused much of the existing fixed-line telecommunication technology, such as switching centers and long-distance communication equipment, minimizing the development costs and leveraging proven technologies. However, GSM introduced a crucial innovation, the ability to wirelessly connect subscribers to the network. In fixed line networks, subscriber connectivity was straightforward, requiring only two dedicated wires per user. And this simplicity was not feasible in mobile environment where users were free to move and change locations dynamically, and GSM had to address several challenges unique to mobile networks. Dynamic subscriber location. In mobile networks, the user's location could change at any time, unlike fixed line networks where a subscriber's physical location was static. GSM required a flexible system to track and manage subscriber locations in real time. And this necessitated the development of mobility management architecture capable of routing calls to a subscriber's current location. Handoff and roaming. During a call, a subscriber might move out of the coverage area of one radio transmitter and into another, and the GSM had to ensure seamless handoffs between cells without disrupting the ongoing call. This required sophisticated software capable of dynamically adjusting the call routing. Switching center modifications. While the hardware of a mobile switching center, MSC, was similar to that of a fixed line switching center, GSM introduced significant software changes. These changes supported functionalities such as subscriber mobility management, call handoffs, and integration with the wireless radio network. And in this figure, you can see how the same hardware could be adapted for fixed line or mobile network use through the different software configurations. Telecommunication equipment vendors like Ericsson, Nokia, Alcatel-Lucent capitalized on this versatility. They offered unified hardware platforms that could be deployed in both fixed line and mobile networks, with the operational role determined solely by the installed software. Virtualized circuit switching. Over the years, the limitations of physical circuit switching became apparent, particularly in terms of scalability and resource efficiency. The rise of packet switching technologies like GPRS and later LTE introduced more flexible methods for transmitting voice and data. In modern GSM networks, physical circuit switching has largely been replaced or complemented by virtual circuit switching over IP-based broadband connections. This transition allows for efficient resource utilization. Network resources are allocated dynamically, reducing idle time during voice calls. Scalability. So virtualized switching can handle higher traffic volumes with fewer hardware requirements. Integration with modern networks. So IP-based systems facilitate seamless interoperability with newer technologies like LTE and voice over IP. The virtualization of circuit switching represents a significant step forward, ensuring that GSM networks remain viable in a rapidly evolving telecommunication landscape. In the 1990s, voice calls dominated communication. However, today, a broader range of internet-based communication methods has taken precedence, with voice calls remaining important but no longer central. These newer services primarily rely on the Internet Protocol to connect users globally. Unlike traditional circuit switching, where a dedicated channel is reserved exclusively for two parties, IP-based communication uses data packets, each containing a destination address. These packets are routed independently through the network, utilizing shared high-bandwidth links that carry data for multiple users. And this paradigm shift forced network operators to maintain two separate infrastructures, a circuit switch network for voice communication and a packet switch network for internet-based services. Managing these dual networks proved costly and inefficient. prompting the replacement of the circuit switching hardware in the mobile switching centers with media gateways. And this transformation virtualized circuit switching, enabling voice calls to transmitted via IP packets. And the result was unified IP-based networks that eliminated the need for physical circuit switched infrastructure. This approach, standardized under the term Bearer Independent Core Network (BICN), streamlined operations and reduced costs. But despite this shift, the core functioning of GSM remained largely intact. But the key change occurred in the lower protocol layers responsible for call signaling and voice transmission. Over time, IP-based communication extended into GSM radio network, particularly with the advent of multi-technology based stations supporting GSM, UMTS, LTE, and 5G NR. And today, such base stations typically connect the core network via a single IP link, simplifying infrastructure management. But for mobile devices, the GSM Air interface, the communication link between devices and the network, remained unchanged during this transition. From a user's perspective, the move from circuit switching to IP-based transition was seamless as it primarily affected the underlying network infrastructure. The telecommunication industry is characterized by fierce competition among network infrastructure manufacturers striving to secure contracts with telecommunication operators. And to enable seamless interoperability and ensure consistent communication capabilities worldwide, the standardization of interfaces and processors is essential. And without international standards, global communication would face significant barriers. For instance, making phone calls across borders would be impractical, and operators would be locked into proprietary systems provided by the first vendor they have partnered with, severely limiting flexibility and growth opportunities. The International Telecommunication Union plays a pivotal role in defining and maintaining global telecommunication standards. And one of its most popular and influential standards discussed in further in next lecture is signaling system number 7, a protocol essential for call routing and interconnectivity between networks. However, in the early days of standardization, many ITU guidelines served only as a basic framework for the lowest common denominator, with individual countries introducing national extensions to suit their specific needs. While these extensions helped localize services, they created challenges for global equipment manufacturers who had to adapt their software and hardware to each country's unique requirements. And of course, this fragmentation led to significantly higher software development costs and integration complexities, especially when interconnecting networks from different countries. And the introduction of the global system for mobile communications, GSM, marked a turning point. And for the first time, a common wireless standard was adopted across Europe. And of course, GSM's success in Europe prompted its adoption worldwide, making it the first truly global standard for mobile communication. And this widespread acceptance brought several key benefits. International roaming. Subscribers could use their devices seamlessly in any GSM network with a roaming agreement, eliminating the need for network-specific devices. It also was a very cost efficient, so manufacturers could produce hardware and software on a large scale with only minimal adjustments needed for local markets to significantly reduce research and development expenses. And it also was the interoperable, so the standardized framework enabled devices from different manufacturers to work together without issues. And the development of GSM was spearheaded by the European Telecommunications Standards Institute, ETSI, an organization responsible for creating and maintaining numerous telecommunication standards. ETSI's GSM standards are compiled into a series of technical specifications, each focusing on a specific aspect of the system, such as radio access, core networks, and interfaces. And these documents serve as a valuable resource for those seeking detailed information about GSM's architecture and functionality. The success of GSM laid the groundwork for subsequent innovations. To oversee the evolution of mobile communication, the third generation partnership project 3GPP was established as a global organization. European Telecommunication Standards Institute became one of the regional members of 3GPP, which now manages the development and maintenance of GSM, UMTS, LTE, and 5G standards. By centralizing efforts under 3GPP, the industry achieved a unified approach to advancing mobile technologies, ensuring global compatibility and reducing fragmentation. And today, all 3GPP documents are freely accessible online via ETSI and 3GPP, enabling researchers, engineers, and developers to stay updated with the latest advancements. In traditional circuit switch telecommunication networks, data transmission was organized into discrete channels. The smallest unit of transmission was the digital signal level 0, DS0 channel, which operated at a fixed speed of 64 kilobit per second. As the S0 channel could be used to transmit either voice or data, making it versatile in its applications. So instead of being referred to as speech channel, it was commonly called a user data channel, reflecting its broader utility. Higher transmission speeds were achieved by combining multiple DS0 channels. So in Europe, the standard for such aggregation was the E1 connection, while in the United States, the equivalent was T1 connection. So both types of connections relied on twisted pair of coaxial copper cables, but different in their capacities. An E1 connection had a gross data rate of 2.048 megabits per second, divided into 32 time slots, each 64 kilobits seconds in size. But one time slot was reserved for synchronization, leaving 31 time slots available for data transmission. A T1 connection offered a gross data rate of 1.544 megabit per second, divided into 24 time slots, with one reserved for synchronization and 23 time slots available for data. However, in practical deployments, some of these available time slots were allocated for signaling system number 7 signaling, further reducing the number of time slots for user data. You can see here. And so SS7 played a critical role in call setup, routing, and network management, making it an indispensable part of telecommunication networks. And for applications requiring higher capacity, an E3 connection was introduced, providing a data range of 34.368 megabit per second and supporting 512 DS0 channels. So this was achieved using advanced multiplexing techniques over twisted pair or coaxial cables. To meet the demands of long-distance communications and high-capacity networks, optical transmission systems based on the synchronous transfer mode (STM) standard were adapted. So, synchronous transfer mode offered a significantly higher transmission speeds and was particularly well suited for intercity and international communication. In the illustration you can see on the screen, there's an overview of STM transmission speeds and corresponding number of DS0 channels supported. And these speeds were achieved using fiber optic cables, which offered unmatched bandwidth, reliability, and resistance to electromagnetic interference. Transition to IP-based networks. So the rise of packet switch networks brought a paradigm shift in telecommunications. So instead of using circuit switch technology with fixed channels, modern networks rely on virtual circuit switching over IP. This transition was facilitated by widespread adoption of Ethernet as a standard for IP-based communication over both the copper and fiber optic cables. Ethernet-based systems offer several advantages: high speeds, transmission speeds of 1 gigabit per second and higher are common, making them ideal for data-intensive applications. It offers cost-effectiveness as advantage, like standardized Ethernet technology enables the production of affordable network equipment, reducing overall infrastructure costs. And it also offers flexibility, so Ethernet supports both local area networks and wide area networks, making it versatile for various use cases. In modern networks, optical Ethernet links are predominantly used for interconnecting network nodes, ensuring high speed, scalable, and cost-efficient communication. The adoption of Ethernet as the de facto standard has significantly simplified network design and reduced operational complexity. For establishing, maintaining, and clearing a connection, signaling information must be exchanged between the end user and network devices. So the signaling process enables the network to manage communication sessions effectively from the moment a call or connection is initiated to its termination. In traditional fixed-line networks, analog telephones signaled their connection request in a straightforward way. When the receiver was lifted off the hook, it indicated to the network that a connection was being requested, and the phone number was sent to the network through one of two methods. Pulse dialing, this involved the phone sending a series of electrical pulses corresponding to the dialed numbers. Each digit was represented by a specific number of pulses. And dual tone multi-frequency, DTMF dialing, also known as tone dialing. This method used a combination of two tone frequencies to represent each number. So it was faster and more reliable than pulse dialing. With the advent of fixed-line ISDN phones and GSM mobile phones, signaling evolved significantly. So instead of relying on the same physical channel for both signaling and voice, modern systems use a dedicated signaling channel for exchanging control information. For example, information such as the destination phone number and call setup parameters are sent as digital messages through this dedicated channel, enabling faster and more efficient communication. The SS7 protocol is also integral to GSM networks and has been enhanced by the European Telecommunications Standards Institute (ATSI) to address the unique needs of mobile communication, such as subscriber mobility management, tracking and updating a subscriber's location as they move. The SS7 standard defines three primary types of network nodes that perform distinct roles. Service switching points, SSPs. SSPs are switching centers, also referred to as network elements, that handle the setup, transport, and forwarding of voice and data connections. These are responsible for initiating and terminating calls and managing the signaling required for these tasks. Service control points, SCPs. SCPs are specialized databases equipped with application software to influence the connection process. For example, in GSM networks, SCPs store the current location of a subscriber. During a call setup to a mobile user, the switching center queries the SCP to determine the subscriber's current location to forward the call accordingly. And this functionality is crucial for mobile communication and is detailed further in next sections of our course. Signaling transfer points, STPs. STPs serve as intermediates that forward signaling messages between SSPs and SCPs. not all nodes in network are directly linked. So STPs ensure messages reach their destinations efficiently, functioning similarly to IP routers in the internet. However, unlike IP routers that handle all types of packets, STPs only forward signaling messages necessary for establishing, maintaining, and clearing calls. But the actual voice and data are carried on separate dedicated links between SSPs. The general structure of an SS7 network includes STPs, SCP databases, and SSP switching centers interconnected to enable seamless signaling and communication. The arrangement ensures that signaling messages traverse the network efficiently, even when the multiple nodes are involved. While SS7 was initially designed for circuit switch networks where a dedicated path is established for the duration of a call, it has also been adopted for virtual circuit switch networks such as those operating over IP. In IP-based networks, signaling messages are no longer confined to dedicated time slots on an A1 link. Instead, they are encapsulated within IP packets and transmitted across the network. The adaptation allows SS7 to function in modern communication infrastructures, bridging the gap between traditional telecommunication networks and newer IP-based systems. But don't worry, in this lecture and also next lectures of our course, we will explore the SS7 protocol stack in greater detail, and we will discuss how SS7 messages are transported over IP networks, illustrating the protocol's versatility and continued relevance in evolving communication systems. So, the key takeaways from these informations is SS7 enables seamless communication by managing signaling between various network nodes. It has evolved from analog pulse and signaling to a sophisticated protocol capable of handling modern telecommunication demands, including mobile subscriber mobility. The SS7 protocol stack supports both traditional circuit switch networks and modern IP-based systems, showcasing its adaptability. The signaling system number 7 is a set of telecommunication protocols that plays a critical role in managing and controlling telecommunication networks. To understand SS7 better, we can use the well-known open system interconnection USI 7-layer model as a reference. The USI model provides a standard framework for describing communication protocols across different layers, which you can see in this illustration, alongside the SS7 and TCP/IP protocol stacks. And at the very foundation of the stack is MTP1, which is Message Transfer Part 1, which corresponds to the physical layer in the USI model. So this layer defines physical properties of the transition medium, such as type of cables, like copper, fiber optics, and so etc., signal levels, electrical or optical, and transmission speeds, measured in bits per second. For example, imagine you are setting up telecommunication network. The physical layer ensures that the infrastructure, like the type of cables and signal properties, meets the requirements for reliable data transmission. And moving up, the data link layer is implemented by the MTP, Message Transfer Part 2, and its primary role is to manage the framing of data into packets and ensure proper synchronization between sender and receiver. Key responsibilities include framing messages into packets. This includes marking the start and end of each packet, error detection and correction. This ensures that the error introduced during transmissions are identified and corrected when possible. So you can think of this layer as a traffic officer, ensuring that all vehicles, which is data packets, have proper identification and follow their assigned routes without collision. The network layer is represented by the MTP3, Message Transfer Part 3. This layer handles the crucial task of packet routing, ensuring the data reaches its intended destination. So functions of MTP3 include assigning source and destination addresses to packets and forwarding packets across different network nodes. Instead of IP addresses as used in TCP/IP, MTP3 utilizes point codes to identify network nodes. These point codes serve the same purpose, but are specific to the SS7 system. For example, when a call or message is transmitted, MTP3 protocol ensures it is routed to the correct telephone exchange or service. From layer 4 to 7 of the OSI model support a variety of SS7 protocols depending on the application. And here's an overview. ISUP, Integrated Services Digital Network User part. So the ISUP protocol is used to manage call setup, control, and teardown. For instance, when a mobile subscriber, for example, party A, initiates a call to a fixed line subscriber, let's call it party B, ISUP facilitates the exchange of messages required to establish the call, alert the recipient, maintain the connection during the conversation, tear down the connection when the call ends. Now you can see the example call flow in this illustration. Party A dials party B's number. The mobile switching center of party A analyzes the dialed number and detects that it belongs to a fixed line network. Then call is forwarded. If the mobile switching center and fixed line switch are directly connected, the call can be routed directly. Otherwise, intermediate nodes such as signaling transfer points, STPs, handle the routing. The mobile switching center sends an initial address message, IM, to the fixed line switch, indicating the call number and desired channel. Then the fixed line switch sends an address complete message, ACM, back to the mobile switching center to confirm that party B is being alerted. Then conversation begins. When party B answers, the fixed line switch sends an answer message, ANM, to the mobile switching center, enabling the conversation. When either party hangs up, a release, REL, message is sent, followed by release complete confirmation. Signaling connection and control part. SCCP operates on layer 4 and serves a function similar to TCP/UDP in the IP world. It manages application identification and routing of non-circuit related signaling. So, by application identification, I mean it differentiates between applications running on the same node using subsystem numbers, SSNs, instead of port numbers. And a routing of non-circuit related signaling, which is essential for database access and messaging services. For example, just as TCP uses port 80 for HTTP and port 21 for FTP, SSCP uses unique SSNs to route incoming messages to applications like billing systems or voicemail services. Transaction Capabilities Application part, TCAP, is used for querying databases in telecommunication networks. It standardizes how messages are structured and exchanged to retrieve information such as subscriber location for call routing, like via home location register, HLR, and service-specific data for applications like roaming or billing. An example use case is when you are roaming internationally. TCAP enables the system to verify your subscription details and ensure seamless connectivity. While SS7 is specifically designed for telecommunication networks, parallels can be drawn with the TCP/IP stack, which is commonly used for internet communications. MTP3 in SS7 is similar to IP in TCP/IP in routing packets, and SCCP in SS7 is very similar to TCP/UDP in TCP/IP in managing sessions and applications. And this comparison helps bridge the gap for students familiar with IP networks, making SS7 concepts more relatable. And that's it with our lecture. The SS7 protocol stack is the backbone of traditional telecommunication networks. enabling reliable signaling for calls, messaging, and database queries. So understanding how its layers correspond to the OSI model provides valuable insight into the architecture of telecommunication systems and prepares students for exploring more advanced topics like signaling security and modern IP-based telecommunication systems. I'm Typhoon and I'm waiting you in the next lecture. Thank you for watching. The GSM network utilizes additional protocols beyond the traditional SS7 protocols used in fixed-line networks. These protocols address the specific requirements of GSM communication. The Mobile Application Part Protocol, standardized in 3GPP, facilitates communication between the mobile switching center and home location register. The home location register maintains subscriber information and is queried by the mobile switching center, for example, to establish a connection to a mobile subscriber. In such cases, the home location register provides information about the subscriber's current location, enabling the mobile switching center to forward the call to the appropriate switching center. This process sets up a voice channel between the mobile switching center and the next hop using the ISUP, which is ISDN's user part message flow, and you can see this in this illustration here. Mobile application part is also essential for communication between two mobile switching centers when a subscriber moves into a new mobile switching center's coverage area during an ongoing call. And as you can see in this illustration, the mobile application part protocol operates over the transition capabilities application part, signal and connection control part, and message transfer part protocols in the lower layers. The BSS map protocol manages communication between the mobile switching center and radio network. It enables functions such as establishing a dedicated radio channel for a new connection to a mobile subscriber. Unlike mobile application part, which is database query protocol, BSS map, which is base station subsystem mobile application part, interacts directly with SCCP bypassing TCAP. The direct transfer application part, DTAP, enables transparent communication between the mobile station and mobile switching center. For example, during a call setup, the mobile station sends a setup message to the mobile switching center containing details such as phone number of the called party. As the mobile switching center forwards this message without processing it, intermediate nodes do not need to understand the DTAP protocol, Direct Transfer Application Part Protocol. And in this illustration, you can see the enhancement of the SS7 protocol stack to meet the GSM requirements. Modern GSM networks employ IP-based transmission for SS7 signaling messages, replacing the traditional MTP1 and MTP2 layers with IP and transport medium-specific protocols, such as Ethernet. So this adaptation is described in this illustration you can see here, which contrasts the IP-based and traditional SS7 protocol stacks. There's a key features of the IP-based stack here, for example, layer 4 protocols, M3UA, and SIG-TRAN. So UDP or TCP are commonly used here, but the Stream Control Transmission Protocol, SCTP, is specified for SS7 signaling due to its ability to handle multiple simultaneous signaling connections between network nodes. And we also have the MTP3 user adaptation layer, M3UA, replicates the functionality of classic MTP3 layer, ensuring compatibility with higher layer protocols such as SCCP. This makes the transition to an IP-based stack seamless for higher SS7 protocols. And SIG-TRAN. The IP-based SS7 stack is often referred to as SIG-TRAN, a term derived from the IATF working group that defined these protocols. The GSM network consists of three primary subsystems. The base station subsystem, BSS, also referred to as the radio network. So the BSS contains all the nodes and functionalities required to connect mobile subscribers to the network via the radio interface. commonly called the air interface. The network subsystem, NSS, also known as the core network, includes all the nodes and functionalities necessary for call switching, subscriber management, and mobility management. Intelligent Network Subsystem, IN. The IN adds optional functionalities to the network, such as prepaid services. These services allow subscribers to found an account in advance for phone calls, SMS, and internet access. When a prepaid subscriber uses network services, the relevant IN node deducts the charges from their account in real time. The network subsystem is crucial part of mobile communication system that manages call switching, call control, and routing between mobile switching centers, other telecommunication networks, and subscribers. The network subsystem also supports subscriber management functions such as registration, authentication, mobility management, and location updates. In this lecture, we will delve into these components and interfaces of the classic NSS, which is Network Subsystem architecture, and its modern IP-based network subsystem counterpart, as represented in this first and second illustrations. Each figure highlights the structure, interfaces, and nodes necessary for communication, emphasizing the evolution of these elements over time. The classic network subsystem relies on circuit switch connections using dedicated E1 lines for communication between its nodes. The key nodes and interfaces in this architecture are mobile switching center, gateway mobile switching center, base station subsystem, visitor location register, home location register, and public switched telephone network. And these elements are interconnected through standardized interfaces, which include A interface, E interface, C interface, and D interface. Each of these interfaces plays a vital role in managing call setup, routing, signaling, and subscriber information. Now let's explore each component and interface in detail. The mobile switching center is the central component of the network subsystem in a classic mobile network. It performs several key functions: call switching, call control, mobility management, and SMS handling. So the mobile switching center connects calls between mobile subscribers and also routes calls to external networks such as PSTN. And it manages call setup, routing, and teardown, ensuring smooth call establishment and termination. The mobile switching center handles mobility management tasks such as handovers when a subscriber moves between cells and location updates when no active connection exists. The mobile switching center forwards SMS messages between subscribers, so it also handles the SMS. And the mobile switch center is connected to other components of the network through specific interfaces. Now here you see the A interface. This connects the mobile switching center to the BSS, so it carries both signaling and voice data, allowing communication between mobile devices and the core network. And here in the E interface, link to the mobile switch center to other mobile switch centers, enabling handovers and car routing across different regions. This ICUP protocol establishes a speech path, while the MAP protocol handles mobility signaling. And here you can see the C interface. This is a signaling only interface between the mobile switching center and HLR, which contains subscriber information. And in the D interface, this connects the mobile switch center to the VLR, allowing temporary subscriber information to be stored locally. The gateway mobile switching center serves as an entry point and exit point for calls between mobile network and external networks such as PSTN, routing of incoming calls and routing of outgoing calls. So when a call is directed to a mobile subscriber, the gateway mobile switching center queries the HLR to determine the subscriber's current location and routes the call to the appropriate mobile switching center. But for the outgoing calls, the gateway mobile switching center acts as a bridge, forwarding the calls to the appropriate external network. The gateway mobile switching center also interacts with the VLR and HLR through the C interface and the D interface. Base station subsystem connects the radio access network to the mobile switch center. It consists of two main components. Base transceiver station, BTS. The BTS handles radio communication with mobile devices, including signal transmission and reception, and also base station controller, BSC. The BSC manages multiple BTSs, handling tasks such as radio resource management, handovers with the same mobile switching area, and traffic load balancing. And you can see this A interface between the BSS and mobile switching center enables voice and signaling traffic to flow seamlessly. The Visitor Location Register, VLR, is a database temporarily storing subscriber information for mobile users within its coverage area. So, when a subscriber enters a new mobile switching area, their details such as IMSI, MCISDN, and current location are copied from the home location register to the visitor location register. The visitor location register supports mobility management, including location updates, authentication, and account handling. So it ensures the network knows the subscriber's current location, it verifies the subscriber's identity before establishing a connection, and it assists the mobile switching center in managing incoming and outgoing calls. The home location register. The HLR is a central database that stores permanent subscriber information, including subscriber identity, IMSI, MCISDN, service subscription details, and current location, which is associated with the mobile switching center and VLR. The home location register interacts with the mobile switching center via the C interface, as you can see here, providing subscriber data for call routing and mobility management. Public Switched Telephone Network, PSTN. The PSTN represents the traditional fixed line telephone network. The gateway mobile switching center interfaces with the PSTN, enabling calls to and from external networks. And now let's basically summarize what we have seen here. So here the A interface connects mobile switching center to base station subsystem, which carries voice and signaling. And here on the top you can see here the E interface connects mobile switching center, but actually they disconnects multiple mobile switching centers, supports handovers and call routing. And in the C interface, you can see on the middle of the triangle, it is signaling only link between mobile switching center and home location register. And lastly, in the D, on the right bottom, you can see this connects the mobile switching center to visitor location register for temporary subscriber data. And with the advancements in telecommunications, the classic network subsystem has transitioned to an IP-based architecture. This evolution brings increased flexibility, scalability, and cost efficiency, while still retaining the fundamental functionalities of the classic network subsystem architecture. This IP-based network subsystem introduces new components and interfaces, including mobile switching center server, media gateway, serving gateway, and IP-based interfaces. And now let's examine these components and their interactions in detail. Mobile switching center server replaces the traditional mobile switching center in an IP-based network subsystem. It is responsible for call control, mobility management, and subscriber management functions, while the actual switching of voice traffic is offloaded to the media gateway (MGW). And key responsibilities of the mobile switch center server include call setup, routing and control, authentication and location updates, coordination of handovers, and management of subscriber data through interactions with visitor location register and home location register. The mobile switching center server interfaces with other components using IP-based links, as you can see on this illustration. You can see in NC interface, this connects mobile switching center server to the media gateway for signaling and call control. And you can see the C and D interfaces connect mobile switching center server to the visitor location register and home location register, ensuring subscriber data is accessed and updated. The media gateway MGW, the MGW handles the actual switching of voice and data traffic. It bridges circuit switched and packet switched networks, converting signals as needed. And here, as you can see in this illustration, the NB interface connects media gateway to the other media gateways for voice traffic exchange. And in this MC interface, this links media gateway to the mobile switching center server, enabling communication between call control and switching functions. And the separation of call control, which is mobile switching center server, and media switching, which is media gateway MGW, enhances flexibility and scalability, as multiple media gateways can operate under the control of single mobile switching center. In modern architectures, the SGW serves as a packet data gateway, enabling the transfer of data services, for example, LTE and 5G over IP-based networks. Integration with IP networks. So serving gateway, SGW, interacts with packet core networks to route IP-based traffic, and it also helps with support for multimedia services, ensures the delivery of voice, video, and data services seamlessly. The IP-based NSS replaces traditional circuit-switched E1 links with IP interfaces, such as NC, MC, and NB, which provide higher capacity and greater flexibility. And as you can see in this illustration, the A interface at the top remains between the BSS and mobile switching center server, but may use IP for signaling. And this NB interface facilitates the media gateway to media gateway communication for media traffic, and this MC interface links mobile switching center server to media gateway for controller signaling, and this NC interface supports communication between mobile switching center server instances. The evolution of the network subsystem from a classic circuit-switched architecture to an IP-based architecture reflects the growing need for flexibility, scalability, and efficiency in modern telecommunications. The classic network subsystem relied on dedicated E1 connections and centralized mobile switching centers, while the IP-based network subsystem leverages mobile switching center servers, media gateways, and IP interfaces to enhance performance and support advanced services like data and multimedia. But both architecture plays a pivotal role in ensuring call establishment, routing, and subscriber management, with the IP-based network subsystem paving the way for next-generation mobile networks such as LTE and 5G. The Visitor Location Register is a crucial component in mobile telecommunication networks, particularly within the GSM architecture. It temporarily stores information about subscribers currently within the coverage area of a specific mobile switching center, and this setup reduces signaling between the mobile switching center and the home location register by maintaining local copies of subscriber data, facilitating efficient call setup and service delivery. Key functions of the visitor location register is subscriber data management, location tracking, service authorization, and roaming support. Subscriber data management. The visitor location register stores essential subscriber information, including the International Mobile Subscriber Identity (IMSI), mobile station ISDN number, and details about subscriber services. This data enables the network to verify and manage subscriber access to various services. As subscribers move, the visitor location register updates their location information, ensuring accurate routing of incoming calls and messages. And when a subscriber enters a new mobile switching center area, their data is transferred to the new visitor location register, and the previous visitor location register deletes the subscriber's record after a fixed period of inactivity. Service authorization. The visitor location register maintains information about the services a subscriber is permitted to use and any restrictions in place, such as banning outgoing calls while allowing incoming ones. This ensures compliance with subscriber agreements and prevents unauthorized service usage. Roaming support. When a subscriber roams outside their home network, the visitor location register collaborates with the home location register to manage roaming permissions and service continuity, ensuring seamless connectivity across different network areas. While the VLR can be implemented as a separate hardware component, it is commonly integrated as a software module within the mobile switching center. This integration is feasible because mobile switching center and visitor location register utilize different signaling connection control part SCCP subsystem numbers SSN and allowing them to operate on a single physical node. The interaction between the visitor location register and other network components is standardized through specific interfaces. In the B interface, this connects the mobile switching center to the visitor location register, facilitating the exchange of subscriber information and signaling messages. In the D interface, this connects to the visitor location register to the home location register, enabling the transfer of subscriber data when the user moves between the different mobile switching center areas. These interfaces ensure efficient communication and data management across the network, supporting seamless mobility and service delivery for subscribers. The Home Location Register is a central database in GSM networks that stores comprehensive information about each subscriber authorized to use the network. It plays a pivotal role in managing and authenticating subscribers, facilitating seamless communication and mobility across the network. Key functions of the Home Location Register is subscriber information management, authentication and security, location tracking, and service profile management. The Home Location Register maintains detailed records for each subscriber, including personal information, service subscriptions, and preferences. And this data ensures that subscribers have access to the services they have opted for and are restricted from those they haven't. And by storing the International Mobile Subscriber Identity, IMSI, and associated authentication keys, the Home Location Register verifies the identity of subscribers attempting to access the network, ensuring secure communication. The Home Location Register keeps track of the current location of subscribers by recording the identity of the visitor location register or serving GPRS support node SGSN managing the subscriber. And this information is crucial for routing incoming calls and messages to the correct destination. And lastly, service profile management stores data related to supplementary services like call forwarding, call barring, and ensuring that ensures these services are appropriately applied based on the subscriber's profile. And these are the key functions of the home location register. And the International Mobile Subscriber Identity. IMSI is a unique identifier assigned to each subscriber in a GSM network. Now, as you can see in this illustration, it consists of 3 parts. Mobile country code at the left. This is a 3-digit code representing the subscriber's home country. Mobile network code at the middle, MNC. This is a 2 or 3-digit code identifying the subscriber's home network within the country. And mobile subscriber identification number, MSIN. The remaining digits uniquely identifying the subscriber within the mobile network. The Mobile Station International Subscriber Directory Number, MSI-SDN, is the phone number associated with the mobile subscriber. Now you can see here the country code up to 3-digit representing the country. National destination code, typically 2 to 3 digits identifying the subscriber's operator or region within the country. And subscriber number, this is a unique number identifying the subscriber within the network. And how they interact with other network components. So Mobile Switching Center, MSC, the home location register, communicates with the Mobile Switching Center to facilitate call routing and mobility management. Visitor location register, when a subscriber roams into a new area, the home location register provides the visitor location register with the subscriber's profile to ensure service continuity. And for the authentication center, the home location register collaborates with the authentication center to authenticate subscribers and secure network access. So, in summary, the home location register is integral to the functioning of GSM networks, ensuring that subscribers are authenticated, their services are managed, and their location is tracked to provide seamless mobile communication. The Authentication Center is a vital component within the GSM network security architecture, responsible for authenticating subscribers and ensuring confidentiality of their communication. It works closely with the home location register to manage and verify subscriber identities, preventing unauthorized access to the network services. There's 2 key functions of the Authentication Center, which is storage of secret keys and generation of authentication triplets. So each subscriber is assigned a unique authentication key known as key I, which is securely stored in both the Authentication Center and subscriber's SIM card. So the key I is never transmitted over the network, ensuring its confidentiality. And by the generation of authentication triplets, I mean during the authentication process, the Authentication Center generates a set of values called an authentication triplet, comprising a RAND, this is a 128-bit random number used as a challenge to the mobile device, signed response, SRES, a 32-bit response generated by applying the A3 algorithm to the RAND and key I, and key C, ciphering key. This is a 64-bit key derived using the A8 algorithm with RAND and key I, utilized for encrypting the communication between the mobile device and the network. Now you will also learn about integration with the network components, which is home location register. So the Authentication Center is often integrated with home location register, sharing subscriber information to facilitate authentication and service provision. And it works with the Mobile Switching Center as well. The Mobile Switching Center interacts with the authentication center to opt-in authentication triplets and execute authentication process during subscriber access attempts. By implementing these functions and processes, the authentication center plays a crucial role in maintaining the security and integrity of GSM networks, ensuring that only authorized subscribers can access network services and their communications remain confidential. While the most functionality required in the networking subsystem for GSM could be added via additional software, the base station subsystem had to be developed from scratch. So this was mainly necessary as earlier generation systems were based on analog transmission over the air interface, and these did not have much in common with the GSM base station subsystem. The base station subsystem is responsible for handling traffic and signaling between the mobile station and the network subsystem. So it includes two main components: the base transceiver station and the base station controller, BTS and BSC. The BTS handles radio transmission and reception. That's why we call it the base transceiver station, while the BSC, base station controller, manages multiple BTSs and oversees handovers, power control, and channel allocation. And that's why we call it base station controller. In Europe, GSM was initially specified only for operation in the 900 MHz band between 890 and 915 MHz in the uplink direction, and between 935 and 960 MHz in the downlink direction, as shown in this illustration you can see here. So uplink refers to the transmission from the mobile device to the network, and downlink means to the transmission from the network to the mobile device. The bandwidth of 25 MHz is split into 125 channels with a bandwidth of 200 kHz each. And in this illustration, you can see GSM uplink and downlink in the 900 MHz frequency band. And it soon became apparent that number of available channels was not sufficient to cope with growing demand in many European countries. Therefore, the regulating bodies assigned an additional frequency range for GSM, which uses the frequency band from 1710 to 1785 MHz for the uplink and from 1805 to 1880 MHz for the downlink. Instead of total bandwidth of 25 MHz as in the 900 MHz range you seen earlier, the 1800 MHz band offers 75 MHz of bandwidth, which corresponds to 375 additional channels. But the functionality of GSM is identical on both frequency bands, with the channel numbers, also referred to as absolute radio frequency channel numbers, ARFCN, being the only difference here. And it should be mentioned that while the 1800 MHz band was very popular for GSM service for a decade, most network operators have since discontinued GSM service in the 1800 MHz band to make room for LTE. And this was possible due to the declining use of GSM and the reassignment of spectrum in the 900 MHz band to accommodate more than just two networks operators in a country. While GSM was originally intended only as a European standard, the system soon spread to countries in other parts of the globe. In North America, for example, analog mobile networks were used for some time before second generation networks, which included the use of GSM technology, were introduced. So as the 900 MHz and 1800 MHz bands were already in use by other systems, the North American regulating body chose to open frequency bands for the new systems in the 1900 MHz band and later on in the 850 MHz band. The GSM standard is also used by railway communication in Europe and other parts of the world. And for this purpose, GSM was enhanced to support a number of private mobile radio and railway specific functionalities. And this version of GSM is known as GSMR, GSM for railways. So GSMR enables seamless, reliable communication for railway operators and operations, ensuring enhanced safety and efficiency. As GSM-R networks are private networks, it has been decided to assign a private frequency band in Europe for this purpose, which lies just below in the public 900 MHz GSM band. And to use GSM-R, mobile phones need to be slightly modified to be able to send and receive in this frequency range. And GSM-R has become a global standard for railway communication, improving the reliability of signaling and communication systems. The base transceiver stations are pivotal components in GSM networks, serving as the primary interface between mobile devices and the network infrastructure. They facilitate wireless communication, replacing the traditional wired connection in fixed-line networks with radio links, commonly referred to as the air interface. The sharp increase of mobile communication has led to the extensive deployment of base transceiver stations worldwide. For instance, in India, there's been a significant expansion in base transceiver stations and tower deployments to support the growing demand for mobile services. The typical base transceiver stations comprises several key components. Transceivers, responsible for transmitting and receiving radio signals to and from mobile devices. Each transceiver operates on a specific frequency and time slot, enabling multiple simultaneous communications. Power amplifiers amplify the signal from the transceiver to ensure adequate transmission power from communication over the desired coverage area. Combiners combine multiple signals from different transceivers to be transmitted through a single antenna, optimizing the use of antenna resources. Duplexers allow simultaneous transmissions and reception of signals through the same antenna by separating incoming and outgoing signals. Control unit manages the operation of the base transceiver stations, including signal processing, handovers, and communication with the base station controller. Antennas radiate and receive radio signals to and from mobile devices. Antennas can be omnidirectional or directional depending on the coverage requirements. The coverage area of base transceiver stations, known as cell, varies based on several factors, including transmission power, antenna height, terrain, and population density. In practice, cells are categorized based on their size and application. Macrocells provide broad coverage in rural or suburban areas with a radius ranging from several kilometers up to 35 kilometers under ideal connections. Microcells serve densely populated urban areas, covering a radius of a few hundred meters to a couple of kilometers, enhancing capacity and reducing congestion. Picocells, designed for indoor environments like shopping malls or airports, covering areas a few dozen meters to improve indoor coverage. And lastly, femtocells, intended for residential or small business use, providing a coverage with a home or office environment. To maximize the efficient use of the limited frequency spectrum, GSM networks employ a strategy called frequency reuse. This involves assigning the same frequency channels to multiple channels that are sufficiently spaced apart to minimize interference. So, the reuse pattern is carefully planned to ensure optimal coverage and capacity while mitigating the risk of co-channel interference. To further enhance capacity and manage interference, base transceiver stations often utilize sectorization, dividing the cell into multiple sectors, each served by its own set of antennas and frequencies. So two-sector configuration, as the name implies, divides the cell into two 180-degree sectors, commonly used along highways or railways to provide elongated coverage areas. And three-sector configuration splits the cell into three 120-degree sectors, a prevalent setup in urban and suburban areas to balance coverage and capacity efficiently. And in high capacity scenarios, we use the six-sector configuration. So cells may be divided into six 60-degree sectors to further increase capacity and reduce interference. Advancements in technology have led to the development of more sophisticated base transceiver stations architectures. Software-defined radios enable dynamic reconfiguration of the base transceiver stations to support multiple standards, like GSM, UMTS, LTE, through software changes, enhancing flexibility and future-proofing the infrastructure. Remote radio heads allow the separation of the transceiver from the baseband unit, facilitating distributed deployment and improving coverage in challenging environments. Massive multiple input, multiple output, and beamforming incorporate multiple antennas to focus the transmission and reception of signals, increasing capacity and coverage, particularly in 5G networks. Effective deployment of base transceiver stations requires careful consideration of various factors: site acquisition and infrastructure, so selecting the appropriate locations for base transceiver stations installation, considering factors like accessibility, power availability, and structural support for antennas. Regulatory compliance, adhering to local regulations regarding electromagnetic emissions, zoning laws, and environmental impact assessments. Black hole connectivity, establishing reliable connections between the base transceiver stations and core network, utilizing microwave links, optical fiber, or other transmission mediums to ensure seamless data flow. Power supply and backup systems, ensuring uninterrupted operation through the robust power solutions, including backup generators and battery systems to handle power outages. Regular maintenance and optimization are crucial to sustain base transceiver stations' performance. Routine inspections, assessing physical and operational aspects of the base transceiver stations to identify and rectify potential issues proactively. Software updates, implementing the updates to enhance functionality, security, and compliance with evolving standards. Performance monitoring, utilizing network management systems to monitor key performance indicators and optimize parameters for improved service quality. So in summary, the base transceiver stations is a cornerstone of GSM networks, enabling wireless communication by bridging mobile devices with a broader network infrastructure. Its design, deployment, and maintenance are critical to ensuring reliable and efficient mobile services across the world. The transition path between base transceiver stations and mobile device is referred to in the GSM specifications as the air interface or the UM interface. It is the critical link that facilitates wireless communication within the GSM network. This interface underpins the entire GSM communication process, enabling voice, data, and signaling transmission in a structured and efficient manner. To allow the base station to communicate with several subscribers simultaneously, two methods are employed. Frequency division multiple access FDMA. Here, user communicates with the base station on a different frequency. And when it uses the time division multiple access TDMA, here GSM uses carrier frequencies with a bandwidth of 200 kHz, over which up to 8 subscribers can communicate with the base stations simultaneously. Subscribers are time multiplexed by dividing the carrier into frames with durations of 4.0 615 milliseconds. So each frame contains 8 physically independent time slots, each allocated for communication with a different subscriber. And the time frame of a time slot is called a burst, which lasts 577 microseconds. For instance, if a mobile device is allocated time slots number 4 for a voice call, the device sends and receives only during this burst and waits for the next frame before sending again. By combining frequency division multiple access and time division multiple access, the total capacity of a base station can be approximated. For example, a base station split into 3 sectors, each equipped with 3 transceivers, provides 24 time slots per sector. 2 time slots are usually reserved for signaling, leaving 22 time slots for user channel per second. Assuming 4 time slots are used for packet switched GPRS services, 18 time slots remain for voice calls per sector, resulting in 54 simultaneous channels per base station. However, a base transceiver station serves a significantly larger number of subscribers as they do not all communicate simultaneously. And the network dimensioning relies on theoretical call profile model with assumptions such as an average of 3 minutes per hour of active usage per subscriber. Based on this, a base station with 54 channels can potentially serve 1080 subscribers. Each TDMA frame is divided into bursts, and each burst has distinct sections, as you can see here. Guard time prevents overlap of signals from subscribers at varying distances. Training sequence compensates for interference caused by reflection, absorption, and multipath propagation. Tails mark the beginning and end of the burst for accurate detection. User data fields contain the digitized voice signal, each with 57 bits, totaling 114 bits of user data per burst. Stealing bits indicate whether user data is present or if the burst is used for signaling. And frames are grouped into multi-frames for efficient signaling and data management. Now, 51 frame multi-frame used for signaling channels like broadcast control channel, and 26 frame multi-frame used for data channels like the traffic channel. Logical channels are mapped to physical time slots and categorized as hellos. Traffic channel transmits digitized voice or circuit switch data. It can also carry low-rate data services. Fast associated control channel used for urgent signaling like handovers by stealing bursts from traffic channel. This ensures critical instructions can be sent without delay. Slow associated control channel reports signal quality for handovers and power control. Additionally, it manages timing advance values to align subscriber transmissions correctly. Standalone dedicated control channel handles all establishment, location updates, and SMS. This channel is crucial before a traffic channel is assigned. And for the common channels, we have broadcast control channel. This transmits essential network information, including cell identifiers and neighboring cell frequencies, enabling mobile devices to perform seamless cell selection and handovers. Paging channel notifies idle subscribers of incoming calls or messages. The paging message includes subscriber identifiers like IMSI or TMCI. Random access channel, used by mobile devices for initial network access. Since multiple devices may attempt access simultaneously, collisions are managed using randomized retransmissions. Access grant channel assigns dedicated channels to mobile devices during connection establishment, ensuring efficient resource allocation. To mitigate interference and improve transmission quality, GSM employs frequency hopping, where the carrier frequency changes with each burst. This reduces the impact of interference, ensuring better signal quality. Up to 64 frequencies can be used for hopping per base station. This technique enhances resilience against interference and ensures more consistent service quality. As the radio signals travel at the speed of light, the distance between the mobile device and the base station can introduce delays. Timing advance ensures that signals from all subscribers within a cell arrive at the base stations in their designated time slots. And without this mechanism, signals from the distant devices might overlap with those from closer devices. Guard times further prevent such overlaps by introducing small idle periods between bursts. ABIS interface, the ABIS interface, connects the base transceiver station to the network, carrying all logical channel information. Initially, an E1 connection with 64 kilobits per second time slots was used. With advancements, physical E1 links are now often replaced by virtual connections over IP-based links, particularly in sites hosting multiple radio technologies like GSM, UMTS, and LTE. Mapping of air interface time slots to the ABIS interface, you can see in this illustration. So this mapping ensures efficient communication and resource utilization, especially in modern multi-technology deployments. The GSM air interface employs robust error detection and correction mechanisms to maintain communication quality. Techniques such as cyclic redundancy checks, CRC, are used to detect errors in transmitted data. Forward error correction FEC mechanisms like convolutional coding help reconstruct lost or corrupted data, ensuring reliable communication even in challenging environments. GSM networks dynamically adjust the transmission power of both the mobile device and base transceiver station to minimize interference and conserve battery life. Additionally, handovers are executed seamlessly as subscribers move between cells. Handover decisions are based on a signal quality measurements reported by the Slow Associated Control Channel SACCH. The organization of frames into multi-frames is critical for managing various types of traffic and signaling. The 51-frame multi-frame structure is used for common channels like Broadcast Control Channel BCCH, while the 26-frame multi-frame is designed for dedicated user channels like the Traffic Channel TCH. So these multi-frames ensures an orderly allocation of resources, balancing signals and user traffic efficiently. Adaptive multi-rate codec improves voice quality and spectrum efficiency by dynamically adjusting the bitrate based on network conditions. Extended coverage GSM, ECGSM, optimized for Internet of Things applications, extending GSM's reach in rural areas with minimal infrastructure. And Edge enhances data transmission speeds using advanced modulation techniques, bridging the gap between GSM and 3D technologies. Now, network operators must carefully plan and optimize their air interface to ensure efficient utilization of resources and high-quality service delivery. Factors such as cell size, frequency reuse patterns, and traffic distributions must be considered to avoid congestion and interference. The GSM air interface is a sophisticated system that combines frequency and time multiplexing to maximize network capacity and quality. Its efficient design, robust error handling mechanisms, and adaptive features have been pivotal in the global success of GSM technology. As GSM continues to evolve, the air interface remains at the heart of its capability to provide reliable and scalable communication services. Thank you for watching. I'm Typhoon and I'm waiting you in the next lecture. Hello everyone, I'm Typhoon and in this lecture you will learn about base station controller. In the architecture of GSM networks, the base station controller or BSC serves as a pivotal component within the base station subsystem. It acts as the intermediary between the base transceiver stations and mobile switching center, managing multiple base transceiver stations and ensuring efficient utilization of radio resources. The base station controller's responsibilities encompass the establishment, release, and maintenance of all connections for the cells under its control, playing a crucial role in a call setup, handovers, and overall network performance. Call and SMS establishment. So, when a subscriber initiates a voice call or attempts to send an SMS, the mobile device begins by sending a channel request message to the network. This process unfolds as like this: channel request. The mobile device transmits a channel request message, typically via the random access channel RACH, to the base station controller. So this message signifies a subscriber's intent to establish a communication channel allocation. Upon receiving the request, the base station controller checks for the availability of a standalone dedicated control channel. If an standalone dedicated control channel, so SDCCH, is available, the base station controller instructs the BTS to activate this channel. Immediate assignment. The base station controller sends an immediate assignment message to the mobile device on the access grant channel AGCH. This message includes the identification of the assigned SDCCH, which is standalone dedicated control channel, enabling the mobile device to proceed with connection setup. And lastly, communication via standalone dedicated control channel SDCCH. So the mobile device utilizes the assigned SDCCH to exchange direct transfer application part DTAP messages, which the base station controller forwards to the MSC. So this exchange facilitates the necessary signaling for call establishment or SMS transmission. For incoming calls or SMS messages, the process is slightly different. It starts with paging. The mobile switch center sends a paging message to the base station controller containing the International Mobile Subscriber Identity, IMSI, or Temporary Mobile Subscriber Identity of the subscriber, along with a location area identifier where the subscriber is currently registered. Broadcasting the page. The base station controller consults its location area database to determine the specific cells where the subscriber should be paged. It then instructs the relevant base transceiver stations to broadcast the paging message over the paging channel. And lastly, the subscriber's response. Upon receiving the paging message, the mobile device responds by sending a channel request message, initiating the process of establishing a dedicated channel for the incoming communication. Traffic channel allocation for voice calls. The allocation of traffic channel for voice communication involves coordination between the mobile switch center and base station controller. Signaling exchange. The mobile device and mobile switch center exchange necessary signaling information via the standalone dedicated control channel to prepare for the voice call. Assignment request. The mobile switch center sends an assignment request to the base station controller, requesting the allocation of a traffic channel for the call. Channel activation. The base station controller verifies the availability of a traffic channel and the designated cell. If available, it instructs the base transceiver station to activate the channel. Notification to mobile device. The base station controller informs the mobile device via the standalone dedicated control channel that the traffic channel has been allocated. The mobile device then switches to the assigned traffic channel and fast associated control channel. Acknowledgement. The mobile device sends a message on the fast associated control channel to confirm the switch to the new channel, which the base transceiver station acknowledges, ensuring the signal is correctly received. And completion. Finally, the mobile device sends an assignment complete message to the base station controller, which in turn notifies the mobile switch center of the successful establishment of the traffic channel, allowing the voice communication to commence. One of the critical functions of the base station controller is managing handovers, ensuring seamless connectivity as subscribers move between cells during an active call. The handover process involves several steps. Signal quality monitoring. The mobile device continuously measures the signal quality of both the current cell and neighboring cells. It reports these measurements to the base station controller via the slow associated control channel. Decision making. The base station controller evaluates the reported measurements to determine if a handover is necessary to maintain call quality. Factors influencing this decision include signal strength, quality, and network load. Preparation. If a handover is deemed necessary, the base station controller selects a target cell and allocates a traffic channel in that cell. It then prepares the new base transceiver station to receive the mobile device. Execution. The base station controller sends a handover command to the mobile device via the fast associated control channel, providing details of the new frequency and time slots. The mobile device synchronizes with the new cell and begins communication on the new traffic channel. Confirmation. The mobile device sends a handover access message to the new base transceiver station, which acknowledges the successful reception. The base station controller then redirects the speech path to the new cell. And lastly, release. After the handover is complete, the base station controller releases the traffic channel in the old cell and informs the mobile switch center of the handover. This notification is for record keeping and does not impact the ongoing call. Power control. Effective power control is essential to minimize interference and optimize network performance. The base station controller manages the transmission power levels of both mobile devices and base transceiver stations. Mobile device power control. The base station controller analyzes signal quality measurements reported by the base transceiver station. Based on these measurements, it instructs the mobile device to adjust its transmission power, ensuring sufficient signal strength while minimizing interference with other cells. This adjustment is communicated via power control messages sent over the slow associated control channel. Base transceiver station power control. Similarly, the base station controller can adjust the base transceiver station's transmission power based on measurements reported by mobile devices. However, power control is not applied to downlink carriers broadcasting common channels like the broadcast control channel, as consistent power levels are necessary for accurate neighboring call measurements by mobile devices. To compensate for the propagation delay caused by a distance between the mobile device and base transceiver station, the base station controller implements timing advance control. Initial access. So when a mobile device first accesses the network, it sends a channel request without knowledge of the appropriate timing advance. The base transceiver station measures the arrival time of this request and estimates the required timing advance, which is then communicated to the mobile device in the immediate assignment message. Ongoing communication in timing advance control. During an active connection, the base transceiver station continuously monitors the timing of the mobile device transmissions. If adjustments are needed due to the changes in the mobile device's location, the base station controller instructs the mobile device to modify its timing advance accordingly, ensuring that the transmissions align correctly within the assigned time slot. In scenarios requiring coverage beyond the standard cell range, such as coastal areas, GSM networks can implement extended range configurations. Time slot configuration. By utilizing every second time slot per carrier, the system allows bursts to overlap into the following empty time slot, effectively doubling the maximum cell radius to approximately 120 kilometers. And capacity trade-offs here, the extended range configuration reduces the number of available communication channels by half, as only alternate time slots are used here. Additionally, mobile devices must have sufficient transmission power to communicate over the increased distance, often necessitating higher powered devices with external antennas. Interfaces and protocols. The base station controller interfaces with various network components through standardized protocols. ABIS interface, This connects the base station controller to the base transceiver station. The ABS interface is responsible for carrying signaling and user data between the base transceiver station and base station controller. So it initially relied on E1 connections with 64 kilobits per second time slot structure, but has since transitioned to IP-based transport for greater flexibility and capacity. A interface connects the base station controller to the mobile switch center. The A interface uses protocols like Base Station System Application Part (BSSAP) for signaling and manages communication for call setup, routing, and mobility. OMC interface links the base station controller to the operations and maintenance center. This interface is used for monitoring, controlling, and configuring network elements, ensuring optimal performance and quick fault resolution. Connection establishment and management. So when a subscriber initiates a service, such as voice call or sending an SMS, the mobile device transmits a channel request message to the network. The base station controller evaluates the availability of standalone dedicated control channel and upon finding one, activates it within the appropriate base transceiver station. Subsequently, the base station controller dispatches an immediate assignment message to the mobile device via the access grant channel AGCH, detailing the assigned standalone dedicated control channel. So the mobile device utilizes this channel to send direct transfer application part DTAP messages, and which the base station controller forwards the mobile switch center for further processing. And for incoming communications, the base station controller receives paging messages from the mobile switch center containing the subscriber's international mobile subscriber identity, IMSI, or temporary mobile subscriber identity, TMSI, and relevant location area here, of course. Leveraging its location area database, the base station controller identifies the specific cells where the subscriber should be paged. Upon the mobile device reception of the paging message, it responds with a channel request, initiating the connection process as previously described. The allocation of traffic channel for voice calls is orchestrated by the base station controller upon receiving an assignment request from the mobile switch center. The base station controller verifies the availability of traffic channel in the designated cell and, if available, activates it within the base transceiver stations. The mobile device is then notified via the standalone dedicated control channel about the traffic channel assignment and switches to the designated channel. To confirm the transition, the mobile device sends a message on the fast associated control channel, which the base transceiver station acknowledges, ensuring both entities are synchronized. The base station controller then informs the mobile switch center of the successful traffic channel establishment, completing the setup for the voice call. The base station controller serves as a critical intermediary between the base station subsystem and network switching subsystem. So it interfaces with the mobile switch center, facilitating the routing for calls, SMS, and data services between mobile users and external networks. The base station controller's role in managing radio resources, handovers, and signaling ensures that the mobile switch center can efficiently handle higher level call control and mobility management functions without being burdened by the complexities of radio interface management. Beyond its real-time communication management responsibilities, the base station controller also oversees various operational and maintenance functions. This includes monitoring the health and performance of base transceiver station units, managing software updates, and collecting statistical data for network optimization. By maintaining the operational integrity of the radio access network, the base station controller contributes to the overall reliability and efficiency of the GSM system. So, the base station controller is a cornerstone of GSM network architecture, orchestrating the complex interplay between mobile devices and the core network. Through its management of radio resources, handovers, power control, and timing adjustments, the base station controller ensures that subscribers experience seamless and reliable communication services. Its ability to adapt to varying network demands and subscriber movements underscores its essential role in the dynamic environment of mobile telecommunications. Hello everyone, I'm Typhoon, and in this section you will learn about GPRS, which is General Packet Radio Service, and EDGE. In the mid-1980s, voice communication was the dominant service in both fixed and wireless networks. As a result, GSM, Global System for Mobile Communication, was primarily designed and optimized for efficient voice transmission. However, in the mid-1990s, witnessed the rapid rise of the Internet, which began reshaping communication needs globally. Recognizing this shift, the General Packet Radio Service (GPRS) was introduced to enhance the GSM standard, enabling efficient data transmission and allowing mobile devices to access the Internet. Subsequently, the introduction of enhanced data rates for GSM evolution (EDGE) further improved data speed and latency, making mobile Internet access more practical and reliable for its time. Initially, GPRS, General Packet Radio Service, and EDGE were well suited for applications like basic web browsing. However, as pages grew more complex and data requirements increased exponentially, the limitations of these technologies became evident. Additionally, the proliferation of devices in mobile networks led to frequent network congestion, especially in areas without LTE, long-term evolution coverage. Now, today, GPRS and EDGE are no longer viable for common tasks like web browsing, even on small screens. In most scenarios, instead, these technologies are now regulated to niche use cases such as legacy systems and embedded devices that transfer minimal amounts of data. Despite their declining relevance, GPRS and EDGE continue to serve specific roles. Embedded devices such as Internet of Things sensors and industrial controllers often rely on these older technologies due to their long replacement cycles. Consequently, many EDGE networks are expected to remain operational for years to support these legacy applications. So as discussed earlier in sections on GSM, the GSM network was originally designed as a circuit switched network. In this approach, all necessary resources for voice or data sessions are allocated at the beginning of the call and remain reserved until the call ends. This mechanism illustrated here. And this offers several key advantages, which is efficient data flow without overheat and guaranteed bandwidth. So once a circuit switch connection is established, data transmission does not require additional signaling or addressing information. Each bit flows seamlessly through the established channel to the receiver without any extra overheat. And for the guaranteed bandwidth band, so circuit switch channels ensure constant bandwidth, making them ideal for applications like voice calls. A steady data rate prevents communication bottlenecks, ensuring smooth and uninterrupted voice quality. And lastly, consistent delay time. Circuit switch networks maintain a constant delay time, which is crucial for voice communication. So variable delays disrupt voice clarity and continuity, necessitating buffers that introduce additional, often unwanted latency. These features make circuit switch data transmission highly effective for voice communication, which requires consistent quality and minimal delay. However, this method presents significant disadvantages for data applications, especially those with variable or bursty bandwidth requirements. While circuit switch networks excel in voice transmission, their efficiency diminishes for data-centric applications. A typical example is web browsing, which involves irregular bandwidth demands. So it has limited data transmission speed. When downloading a web page, maximum bandwidth is desirable for faster completion. However, circuit switch channels provide fixed bandwidth, limiting the speed at which data can be transmitted. It also has inefficiency during idle periods. So after a web page is downloaded, the user typically spends time reading it, during which no data is exchanged. In a circuit switched system, the reserved resources remain idle, resulting in significant inefficiency and wastage. Also, it is suboptimal resource utilization, the inability to dynamically adjust bandwidth in response to varying demands further limits the system's efficiency for modern data services. In summary, while circuit switch transmissions remain optimal for voice communication, its inherent limitations made it unsuitable for growing demands for internet and data services. GPRS and Edge addresses these challenges by introducing packet switch technologies, enabling efficient and scalable data communication. The evolution from circuit switch to packet switch systems marked a significant milestone in the development of mobile communication networks, laying the foundation for modern technologies like 4G and 5G. For burst data applications, where data is transmitted inherently rather than continuously, a more efficient approach than a circuit switching is needed. Instead of reserving a channel for the entire duration of a session, resources are allocated only when the data needs to be sent or received and released immediately afterward. This approach, called packet switching, collects data into packets before transmitting them over the network. Each packet contains a header, which includes information about the sender, source address, and the receiver, which is destination address. These headers enable network elements to route the packets correctly through the network. For instance, in the Internet, the source and destination addresses correspond to the Internet protocol addresses of the devices involved. To enable packet switch data transmission over GSM networks, General Packet Radio Service (GPRS) was introduced as a packet switched extension to the predominantly circuit switched GSM network. While IP packets can be transmitted over circuit switched GSM connection, the benefits of packet switching are lost in such a scenario because the packets remain bound to the limitations of a circuit switch channel until they reach the internet service provider. The GPRS, in contrast, is an end-to-end packet switch network, ensuring that IP packets are transmitted using packet switching through the entire communication process. GPRS was originally designed to accommodate various packet switching technologies. However, the overwhelming success of the Internet, which relies exclusively on the IP protocol for packet switching, led to the IP becoming the sole supported protocol in GPRS network. As a result, terms such as user data transfer, user data transmission, or packet switching, as used in this context, invariably refer to the transfer of IP packets. So in summary, GPRS revolutionized mobile data transmission by introducing packet switching, which efficiently manages bursty data applications. The improvements made by GPRS and later Edge represent a significant milestone in mobile communication technology, paving the way for more advanced systems like 3G, 4G, and beyond. This evolution marked a transition from time-based billing and constant channel usage to flexible, efficient, and user-friendly mobile internet solutions. The Universal Mobile Telecommunications Systems, a milestone in mobile communication technology, faced inherent design limitations by the end of the 2000s. Similar to how GSM and GPRS reached their technological bounds in the 1990s, UMTS had to evolve to meet increasing demands for higher data rates, improved spectrum efficiency, and better user experiences. This need prompted the third generation partnership project, 3GPP, a collaborative effort among mobile device manufacturers, infrastructure developers, and network operators to redesign both the radio and core networks. This redesign resulted in long-term evolution, LTE, introduced in 3GPP Release 8, bringing transformative improvements in multiple areas. When UMTS was developed, its use of 5 MHz carrier bandwidth with wideband code division multiple access (WCDMA) was groundbreaking. However, scaling a wideband code division multiple access to higher bandwidths proved challenging. As the carrier bandwidth increases, the time between transmission steps shortens, making worse multipath fading. So multipath fading occurs when radio waves bounce off objects, causing delayed and overlapping signal arrivals at the receiver, which complicates signal interpretation. LTE addressed these limitations by adopting orthogonal frequency division multiplexing, OFDM, for the downlink. So OFDM divides the data stream into multiple narrowband carriers like 15 kHz each, transmitting them simultaneously. And this approach extends transmission steps, significantly mitigating the effects of multipath fading. Furthermore, LTE adapts to varying bandwidths, supporting configurations from 1.25 MHz to 20 MHz with common usage scenarios employing 10, 15, and 20 MHz channel. And a 20 MHz carrier under optimal conditions can deliver data rates exceeding 100 megabits per second. LTE mandates advanced features for all devices, including support for multiple input, multiple output technology. MIMO enhances data rates by transmitting multiple data streams simultaneously over the same carrier. Additionally, LTE supports two transmission variants, frequency division duplex, which is FDD, and time division duplex, the TDD. So FDD separates uplink and downlink transmissions using distinct frequency bands, while TDD alternates these transmissions on the same frequency. Unlike UMTS, where the time division duplex adoption lagged, LTE seamlessly integrates both modes, ensuring minimal differences in network architecture and enabling hardware and software reuse. Carrier aggregation, CA, introduced in LTE Advanced, further boosts spectrum efficiency. So CA, carrier aggregation, allows the bundling of up to 520 MHz carriers even across different frequency bands, achieving aggregate data rates of several hundred megabits per second. And today, many networks routinely aggregate 3 to 4 carriers, with future standards envisioning even greater aggregation capabilities. One of the LTE's pivotal advancements is its all-internet protocol network architecture. Unlike UMTS, which relied on a circuit-switched core for voice and SMS, LTE employs an entirely IP-based core network, simplifying design and improving efficiency. Even SMS, a legacy service, is transported over IP signaling messages. So this all-IP approach mirrors fixed-line networks like DSL and fiber, where voice telephony transitioned to IP protocols. The introduction of voice over LTE has further enhanced voice services, providing high-quality voice communication without relying on older circuit-switched fallbacks, CSFP mechanisms. And today, most LTE devices and networks support VoLTE, relegating CSFP to specific scenarios such as older devices, international roaming, or areas without LTE coverage. LTE's design eliminates many complexities of earlier systems, and all network node interfaces use IP, making the underlying physical infrastructure interchangeable. So logical and physical network components have been reduced, resulting in lower round-trip delays of 25-30 milliseconds. So optimized signaling accelerates connection setup, enabling quick transitions into and out of power-saving states. So devices achieve network connection within milliseconds and enhancing user experience and energy efficiency. To ensure seamless user experiences, LTE devices are designed to support legacy technologies such as GSM, GPRS, Edge, and UMTS. So this backward compatibility allows seamless handovers between different network types. And similarly, LTE incorporates with CDMA 2000 networks, enabling users to roam across these systems while maintaining IP-based sessions and communication. LTE's introduction in 3GPP Release 8 laid the groundwork for continuous innovation. Subsequent releases such as LTE Advanced and LTE Advanced Pro aimed to meet the ITU's IMT Advanced standard for 4G networks. And key advancements include carrier aggregation, enhanced MIMO configurations, and support for small, power-efficient Internet of Things devices through narrowband Internet of Things, and which caters to devices with minimal data requirements and extended battery life, addressing emerging Internet of Things use cases. LTE's architecture supports efficient network planning and management. Backhaul technologies ranging from fiber to microwave links integrate seamless into LTE's IP-based frameworks, and mobility management ensure seamless transition between LTE, GSM, and UMTS networks, maintaining uninterrupted user sessions. Emerging technologies such as network function virtualization and IPv6 support continue to enhance LTE's capabilities, paving the way for next generation networks, which you will learn in next sections. LTE represents a significant leap in mobile communication technology, addressing the limitations of its predecessors while providing a scalable foundation for future advancements. Its flexible area interface, all IP architecture, and support for advanced features like carrier aggregation and MIMO have redefined the mobile broadband experience. As LTE evolves with innovations like NB Internet of Things and enhanced aggregation, it remains a cornerstone of global wireless communication, bridging the gap to 5G and beyond. Hello everyone, I'm Typhoon and welcome to this in-depth exploration of LTE network architecture and interfaces. The LTE, or Long-Term Evolution Network, represents a massive leap forward in mobile communication technology, offering faster data speeds, lower latency, and seamless connectivity. And today we will uncover how LTE networks are structured, their key components, and how all these parts work harmoniously to deliver the digital experiences we rely on daily. The LTE network architecture simplifies and enhances the design of mobile networks compared to earlier generations like GSM and UMTS. This architecture is divided into two main parts, the radio access network and core network. And unlike other older networks, LTE reduces the number of logical nodes, which streamlines the design and reduces operational costs and latency. Now let's take a look at this illustrated diagram here. Here you can see the core components of the LTE architecture, including the user equipment, eNode B, the mobility management entity, serving gateway, SGW, PDN gateway, PGW, and the home subscriber server, HSS, here illustrated here. And each of these components plays a vital role in ensuring efficient communication, and over the next sections we will examine these elements in detail and their associated interfaces. The user equipment, or UE, is the device used to access LTE networks. Smartphones, tablets, and Internet of Things devices fall into this category, and these devices are equipped with advanced technologies to support high-speed data transmission. And LTE specifications define various user equipment categories, each with different capabilities, of course. Now, for example, category 4 devices can achieve download speeds of up to 150 megabits per second and upload speeds of 50 megabits per second. And for example, category 18 devices, which represent high-end technology, can deliver speeds of up to 1.2 gigabits per second using carrier aggregation and advanced MIMO techniques. The LTE uppercase U, lowercase u interface, you can see in the left bottom of the illustration, connects the user equipment wirelessly to the eNode B, facilitating communication. And a key technology here is MIMO, or multiple input, multiple output, which uses multiple antennas as both the transmitter and receiver ends to improve data throughput and reliability. For example, 2x2 MIMO, multiple input, multiple output, uses two antennas at both ends, while 4x4 MIMO provides even greater performance under optimal conditions. The UU interface isn't just about speed here. It's also crucial for enabling devices to connect to multiple networks seamlessly. Now, modern user equipments often support fallback for UMTS or GSM networks when LTE coverage is unavailable. So this ensures uninterrupted connectivity for calls, messages, and data services. And additionally, modern devices are designed to work across multiple LTE frequency bands, making them versatile and ensuring they are compatible with global deployments. The eNode B, or Evolved Node B, is the base station of an LTE network. Now, it's a powerhouse that handles several critical functions, including managing radio resources, scheduling data transmissions for multiple user equipments, ensuring quality of service, handling mobility management, including handovers, coordinating interference reduction with neighboring cells. Unlike previous base stations in GSM or UMTS you learned earlier in this lecture, the eNode or Evolved Node B is autonomous and integrates functions that were previously handled by centralized controllers like the radio network controller. This autonomy reduces latency and improves network efficiency. And in this illustration, you can see the internal architecture of eNode B, including antennas, radio modules, and digital modules. The evolved Node Bs also use advanced technologies like remote radio heads, RRH, by placing the radio modules closer to the antennas. LTE networks reduce signal loss and improve performance. And another standout feature of eNode Bs is their ability to handle handovers autonomously. When a mobile device moves from one cell to another, the eNode B initiates and executes the handover without relying on the core network. This reduces latency and ensures seamless user experience. These handovers are facilitated by the X2 interface, which connects neighboring eNode Bs directly. Moreover, eNode Bs are equipped to handle interference coordination in dense urban areas where multiple base stations operate on the same frequency bands. eNode Bs communicate with each other to minimize interference and optimize user throughput. This coordination is critical for maintaining the high performance of LTE networks. The core network. The core network ensures seamless connectivity and session management. It comprises several critical components. Mobility Management Entity, MME. This control plane component manages signaling, handles device authentication, and establishes sessions. It also plays a key role in tracking user mobility and coordinating handovers. Serving Gateway, SGW. This user plane component acts as a data anchor during mobility events. It routes and forwards data packets between the user equipment and core network. PDN gateway, also called PGW. So the PDN gateway connects the LTE networks to external networks such as internet. It also manages IP address allocation and enforces key OS policies. And together, these components ensure that users experience consistent and reliable connectivity, whether they are streaming videos, browsing the web, or participating in online meetings. The core network also supports advanced features like IP address continuity, enabling devices to maintain their IP addresses even during handovers. The SGW and PGW also manage the complex task of quality control, whether it's prioritizing real-time applications like video calls or ensuring efficient routing of bulk data transfers. These gateways ensure the user experiences remain smooth and consistent. Interfaces are the glue that binds the LTE networks together. Let's explore the three key interfaces. Now, in this illustration, you can see this one interface, LTE U interface. At the you can see that I wrote it under the LTE text at the left bottom. Yeah, and and X2 interface in the middle, written in light blue. I guess we can call that a light blue. Yeah. Now, let's start with explaining the LTE UU interface. This wireless link connects the user equipment to the eNode B. You can see the connection here. And is the only interface that operates over the air. And S1 interface you can see in the middle under the S11. This interface connects the E node B to the core network, and it also has two logical parts. S1CP, which is control plane, handles signaling for mobility, session management, and authentication, and S1UP, user plane, transports user data using IP tunneling protocols like GTP. Now we also have the X2 here, you can see in the middle. This interface enables direct communication between E node Bs here, and it facilitates fast handovers and coordinates interference management. The X2 interface is particularly vital in urban environments where cells are densely packed. By enabling direct communication between E node Bs, the X2 interface helps minimize interference and optimizes resource utilization. Additionally, the S1 interface ensures that even if the X2 interface is unavailable, handovers can still be managed through the core network. This redundancy is one of the strengths of LTE's design, ensuring reliability under all conditions. LTE networks operate on a wide range of frequency bands to support diverse deployment scenarios. For example, in Europe, common bands include 3 1800 MHz and 20 800 MHz. In the United States, bands like 4 AWS and 12 700 MHz are widely used, and China primarily uses bands such as 38, which is 2600 MHz for TD-LTE. So modern LTE devices support multiple bands, enabling global roaming and ensuring compatibility across regions. However, supporting so many bands poses challenges for antenna design and receiver sensitivity. Another consideration is the allocation of spectrum for different use cases. Now, for instance, low frequency bands like 700 MHz are ideal for rural coverage due to their ability to penetrate buildings and cover long distances. Meanwhile, high frequency bands like 2600 MHz are better suited for urban areas with dense traffic. While LTE promises high-speed connectivity, but the real-world performance depends on several factors, including network congestion, interference from neighboring cells, distance from E node to B. Now, for example, a typical LTE cells operating on a 20 MHz carrier with 2x2 MIMO can achieve peak downlink speeds of 150 megabits per second. However, practical speeds are often lower due to shared resources and environmental conditions. Advanced features like carrier aggregation can help improve real-world performance. By combining multiple frequency bands, carrier aggregation increases the bandwidth available to user equipments, enabling faster speeds and better network utilization. So, to summarize, LTE network architecture is a masterpiece of engineering. It integrates advanced technologies like multiple input, multiple output, carrier aggregation, and IP-based core networks to deliver unmatched performance. From user equipment to the core network, every component plays a crucial role in ensuring seamless connectivity. Thank you for joining this comprehensive look at LTE networks. Stay tuned for more deep dives into the fascinating world of mobile communication systems. I'm Typhoon and I'm waiting you in the next lecture. Hello everyone, I'm Typhoon and welcome to this in-depth exploration of the LTE network components and their key functions. In this lecture, we will delve into the critical elements of LTE architecture that ensure seamless connectivity, user mobility, and efficient data transmission. Whether you are a telecommunication enthusiast or a professional, understanding these concepts is vital to grasping how modern mobile networks operate. At the heart of the LTE core network lies the Mobility Management Entity, or MME. This component serves as the central hub for all signaling exchanges between the E node Bs and the core network, as well as between users and the core network. The mobility management entity's primary role is managing signaling tasks, not user data, which is why its signaling is referred to as non-access stratum signaling. Now let's break down the key responsibilities of the MME, so-called mobility management entity. Authentication. So when a user first connects to the network, the mobility management entity facilitates the authentication process by exchanging information with the home subscriber server or HSS. Authentication ensures that only valid users gain access to the network. Once the user is authenticated, encryption keys are sent to the eNode B to secure further communication. Bearer establishment. Although the mobility management entity does not handle user data directly, it is responsible for setting up IP tunnels between the eNode B and the gateway to the internet. This involves selecting the appropriate gateway when multiple options are available. Bearer establishment is crucial for enabling end-to-end communication between the user and the internet. But there's another critical task of the MME is NAS mobility management. So when a mobile device enters a dormant state to conserve battery, the MME releases the air interface connection but keep track of the device's location within a tracking area. So if data arrives for the device, the MME sends paging messages to all eNode Bs in the area to re-establish the connection. The MME also plays a vital role in handovers. So if the X2 interface between the eNode Bs is unavailable, the MME forwards handover messages and modifies the user data IP tunnel to ensure a seamless transition. Additionally, it supports internetworking with legacy networks like GSM and UMTS, ensuring smooth transitions for devices moving between different radio technologies. Finally, the MME provides support for legacy services such as SMS and voice calls. Despite LTE being a purely IP-based network, these traditional services are still widely used and must be seamlessly integrated into the modern framework. The Serving Gateway, SGW. Next, we have the Serving Gateway. This component is the bridge between the radio network and the core network, ensuring the user data flows efficiently. And the SGW, the serving gateway, handles several critical tasks as well, including but not limited to terminating user plane tunnels. On the radio network side, the serving gateway terminates the S1 up and GTP tunnels from the eNode Bs. On the networking side, it terminates S5 up GTP tunnels to the PDN-GW. So these tunnels are essential for encapsulating user data and ensuring its secure transmission. And the SGW manages the creation, modification, and termination of user data tunnels. So it also has a function of managing the tunnels. So if a handover occurs with the same SGW control, serving gateway control, only the S1 tunnel needs to be updated. However, if the handover involves a new SGW serving gateway, the S5 tunnel must also be modified. So this flexibility ensures seamless data transmission even during complex mobility scenarios. The SGW serving gateway also plays a crucial role in optimizing network performance by balancing user data traffic across multiple gateways. This ensures efficient utilization of network resources even during peak usage periods. The Packet Data Network Gateway, or PDN-GW, serves as the gateway between the LTE network and external networks such as the Internet or private corporate intranets. The PDN-GW Packet Data Network Gateway performs several functions, one of which IP address assignment. So when a mobile device connects to the network, the Packet Data Network Gateway assigns it an IP address. This enables seamless communication with the internet and other external networks. Multiple IP addresses can be assigned to a single device, enabling simultaneous connections for different services such as internet browsing or voice over LTE, VoLTE. Network address translation. So, due to the limited availability of IP version 4 addresses, the Packet Data Network Gateway uses NAT to map multiple internal IP addresses to a few public IP addresses. So, this not only conserves IP resources but also enhances security by blocking unsolicited inbound connections. And roaming support. The Packet Data Network Gateway, PDN-GW, plays a key role in international roaming. So when a user travels abroad, their data traffic is routed through the Packet Data Network Gateway in their home network. So this ensures secure and seamless internet access, a process known as home routing. However, an alternative method called local breakout allows data to be routed through the visited network's PDN-GW, though this is less commonly used here. And in addition to these three roles, the Packet Data Network Gateway provides a critical support for QoS policies, ensuring that high priority applications receive the necessary bandwidth and low latency to function effectively. The Home Subscriber Server, or HSS, is the central repository for subscriber information in the LTE network. So it contains all the data required to authenticate users, manage their services, and track their location within the network. So key responsibilities of the HSS include, but not limited to, storing subscriber identities such as the International Mobile Subscriber Identity, or IMSI, managing authentication data and encryption keys, maintaining information about subscribed services such as voice, SMS, and data access, supporting roaming by providing subscriber information to foreign networks. So by integrating with legacy systems like the Home Location Register, the HSS ensures smooth interoperability between LTE and other networks like GSM and UMTS. This interaction is vital for supporting global roaming and providing users with consistent experience regardless of location. LTE networks rely on several supporting systems to deliver high-quality services. The policy and charging rules. The LTE networks rely on several supporting systems to deliver high-quality services. The policy and charging rules function, or PCRF, is one such component here. So it ensures the real-time applications such as VoLTE receive the necessary bandwidth and low latency to function smoothly. So the PCRF, policy and charging rules function, interacts with the PDN-GW and SGW to enforce quality of service policies based on user subscription and application requirements. And additionally, it plays a role in billing by tracking data usage and ensuring the users are charged appropriately for their network activities. The LTE core network is a marvel of modern engineering, combining advanced technologies and efficient protocols to deliver seamless connectivity. From the MME's signal management to the PDN-GW's internet access, each component plays a vital role in ensuring a reliable user experience. By understanding these components, we can appreciate the complexities and innovations that power the digital world we live in today. Now, thank you for joining us in the exploration of the LTE core network components. Stay tuned for more insights into technologies that power our connected world. My name is Typhoon, and I'm meeting you in next lecture. Hello everyone, I'm Typhoon, and welcome to our in-depth exploration of LTE's frequency division duplex, or FDD, air interface, and its use of orthogonal frequency division multiple access, or OFDM, as you can see in this illustration, for downlink transmission. So this session will also demystify the process visualized in the accompanying diagram, showcasing the brilliance behind LTE's efficiency, scalability, and performance. Now, to appreciate LTE's air interface, let's first look at its predecessors. In GSM, which you learned in previous lectures, data transmission relied on narrow 200 kHz carriers divided into 8 time slots, each handling a single voice call. This configuration worked for voice services, but severely limited data capabilities. UMTS expanded the carrier bandwidth to 5 MHz, employing code division multiple access (CDMA). So this technology supported continuous data streams separated by unique codes. Later, high-speed packet access (HSPA) introduced time slot scheduling to optimize packet switch data delivery. However, CDMA faced limitations when carrier bandwidth increased. Delayed signals caused by multipath interference degraded performance, making CDMA unsuitable for wider channels. And LTE tackled these challenges head-on by introducing an entirely new air interface design. At the core of the LTE's downlink transmission is orthogonal frequency division multiple access, or FDMA, or OFDMA. So, instead of using a single high-speed carrier like UMTS, OFDMA splits data into multiple slower streams, each transmitted over distinct subcarriers. Now you can see this in this illustration. This design brings two key advantages: multipath resistance and spectral efficiency. Multiple resistance: by using slower subcarriers, OFDMA minimizes disruptions caused by reflected signals arriving at different times. And spectral efficiency: multiple subcarriers make better use of available bandwidth, supporting higher data rates and more simultaneous users. Now let's walk you through the process of OFDMA transmission as illustrated in this diagram. At the transmitter, you can see the input data stream and IFFT conversion. So a digital data stream such as 1101.001.1.0.1.0.1 is delivered to the transmission. And then the streams are then processed using the inverse fast Fourier transform, or IFFT, you can see in this block here, converting them from the frequency domain into a time domain composite signal. This step combines the subcarriers into a single waveform. The composite signal is modulated, amplified, and transmitted over the air by the base station's antenna. This ensures robust and efficient delivery of data. Now let's examine the reception process here, shown in the lower half of the diagram. So at the receiver side, we can see the modulation and amplification. The incoming signal is demodulated and amplified. FFT conversion, we can see also that a fast Fourier transform is applied here, converting the time domain signal back into the frequency domain. This step separates the composite signal into its original subcarrier components. And we also have the subcarrier detection, which the receiver detects the data transmitted on each subcarrier. You can see this detect, and reassembly. Finally, the parallel streams are assembled into the original high-speed data streams, such as 1101.001.1.0.1.0.1, and passed to higher network layers. This process ensures that LTE can deliver data reliably and efficiently, even in challenging environments. OFDMA operates using carefully defined physical parameters, which is subcarrier spacing. Each subcarrier is spaced 15 kilohertz apart. It also has a symbol duration. Each transmission step lasts 66.667 microseconds. And it also has the cyclic prefix to counteract interference caused by multipath propagation. A cyclic prefix, a short segment of data, is added before each symbol. In environments with severe multipath interference, an extending cyclic prefix of 16.67 microseconds can be used. However, this reduces data throughput, as fewer symbols can be transmitted in a given time frame. OFDMA scalability is another strength here. LTE supports flexible bandwidth ranging from 1.25 MHz to 20 MHz with a constant 15 kHz subcarrier spacing. For example, a 5 MHz channel uses 300 subcarriers. A 10 MHz channel uses 600 subcarriers. A 20 MHz channel supports up to 1,200 subcarriers. This scalability ensures that LTE can adapt to various deployment scenarios from densely populated urban areas to sparsely populated rural regions. OFDMA's ability to schedule users in both the frequency and time domains makes it highly efficient here. At any given moment, different users can be assigned distinct subcarriers, maximizing resource utilization. And this dual domain scheduling ensures that LTE can support multiple users simultaneously, delivering high-speed data to each while maintaining network efficiency. Compared to GSM and UMTS, LTE's OFDMA offers superior performance here. By splitting data across multiple subcarriers, LTE overcomes the bandwidth limitations of GSM and multipath interference issues of CDMA, ensuring robust and efficient communication. This design makes the LTE a future-proof technology capable of meeting the ever-increasing demands for high-speed data. In conclusion, OFDMA is a cornerstone of LTE's success. Its innovative use of subcarriers, scalability, and efficiency makes it an ideal solution for modern mobile communication. By understanding the principles behind this technology, we can better appreciate the engineering brilliance that powers LTE. So, thank you for joining us in this exploration of LTE FDD air interface, or OFDMA. Stay tuned for more insights into technologies shaping the future of wireless communication. I'm Typhoon and I'm waiting you in the next lecture. Hello everyone, I'm Typhoon and welcome to our deep dive into the technology behind LTE's uplink transmission, Single Carrier Frequency Division Multiple Access, or SC-FDMA. In this lecture, we will explore the intricacies of SC-FDMA, its benefits, and how it addresses challenges specific to uplink transmission. Additionally, we will decode the accompanying diagram to illustrate how SC-FDMA works in practice. LTE's downlink relies on orthogonal frequency division multiple access, or OFDMA, a highly efficient scheme for base station transmissions. However, applying OFDMA directly to the uplink is less ideal. Why? Because OFDMA's high peak-to-average power ratio, or PAPR, can significantly impact power efficiency. Now let's understand this better. The PAPR, or peak to average power ratio, represents the difference between the peak and average power levels in a signal. With OFDMA, the peak power required for the signal is much higher than the average power. This discrepancy forces mobile devices to use more energy to accommodate the peaks, draining battery life. To address this challenge, LTE employs SC-FDMA for uplink transmissions, and as you can see, the architecture of the SC-FDMA in this illustration. And SC-FDMA significantly reduces PAPR, which is, remember, peak to average power ratio, making it more efficient for battery-driven devices. And it achieves this while retaining the advantages of multi-carrier transmissions seen in previous lectures, which is OFDMA. Now let's break down the SC-FDMA transmission process as illustrated in this diagram. So SC-FDMA introduces an additional processing step compared to OFDMA, which lowers the PAPR. So at the first here we have the input signal on the top left, you can see here. This process begins with an input data stream such as 110100110101. And yeah, then it comes to fast Fourier transform or FFT conversion. Now the first step is a fast Fourier transform in the architecture, which converts the time domain signal into the frequency domain, and this step distributes the information of each bit across multiple subcarriers, reducing power differences between them. And we also have the subcarrier mapping, which I didn't draw in this diagram, but it is between the FFT and IFFT here. So next, the frequency domain signal is mapped to a specific subcarriers. And other subcarriers are encoded with zeros to maintain orthogonality and reduce interference. Now we also have the IFFT. This is an inverse fast Fourier transform is then applied to convert the frequency domain signal back into the time domain. This step creates a single carrier signal with much lower PAPR. And we also have the modulation and transmission, or we can also say the modification and amplification. So finally, the signal is modulated, amplified, and transmitted over the air, ensuring efficient and reliable communication with the base station. So SC-FDMA's unique structure ensures that the transmitted signal maintains power efficiency while leveraging the advantages of frequency division. Now let's examine how the base station processes the incoming signal. Now you can see this on the other half of the diagram at the bottom. We first have the demodulation. So the signal is first demodulated to prepare it for further processing. Then we have the FFT conversion, which is an FFT is applied to convert the received time domain signal back into the frequency domain. So the step extracts the data from each subcarrier. And then we have the IFFT for reassembly. The frequency domain signal is then processed with an IFFT, reversing the initial processing at the transmitter. This step reassembles the original time domain signal. And we also have the output. Finally, the reassembled signal is decoded to recover the original data stream, such as 110100110101. And this process ensures that data is transmitted and received accurately, even in more complex environments with multiple users. SC-FDMA's efficiency is particularly evident in real-world scenarios. For instance, battery life. To reduce PAPR means mobile device consume less power, extending battery life, a critical advantage for users in remote areas. Signal reliability. By distributing the data across multiple subcarriers, SC-FDMA ensures robust performance, even in environments with high interference. Spectrum efficiency. SC-FDMA maximizes spectrum utilization, enabling operators to serve more users simultaneously without compromising quality. In summary, SC-FDMA is a cornerstone of LTE's uplink transmission, addressing power efficiency challenges while maintaining robust performance. So its innovative design ensures that LTE remains a leading technology in wireless communication. So thank you for joining us in this exploration of SC-FDMA. Stay tuned for more insights into the cutting-edge technologies powering modern networks. I'm Typhoon and I'm waiting you in next lecture. Hello and welcome. I'm Typhoon and today we're diving deep into a fundamental concept behind LTE's impressive data speeds: quadrature, amplitude, modulation, or QAM. If you have ever wondered how mobile networks manage to deliver high-speed internet, QAM, quadrature, amplitude, modulation is a significant part of the answer. In this lecture, we will explore what QAM is, how it works, and why it is so crucial to LTE technology. We will also connect these concepts to real-world applications and show you why QAM is a cornerstone of modern wireless communication. Let's begin by understanding the big picture of LTE. At its core, LTE achieves high data rates by using a technology called orthogonal frequency division multiplexing. You learned that in the previous lecture, remember? Or we can also call that OFDM. So OFDM divides the available spectrum into numerous narrowband subcarriers, each transmitting data independently. The magic of OFDM is its ability to handle multiple low-speed data streams simultaneously and when combined achieve incredibly high overall speeds. However, the efficiency of these subcarriers depends on the modulation scheme used, and that's where the QAM comes into play. Before diving into QAM, now let's briefly revisit the concept of modulation. Modulation is the process of encoding information onto a carrier wave, which is sinusoidal signal, remember? And there are three primary ways to modulate a wave. Amplitude modulation, or AM, varies the amplitude of the wave to encode the data. Frequency modulation change the frequency to represent the data, and phase modulation, PM, adjusts the phase of the wave for encoding information. QAM combines amplitude modulation and phase modulation to encode data more efficiently. This dual approach allows QAM to encode multiple bits per symbol, significantly increasing data rates compared to simpler modulation schemes like binary phase shift keying (BPSK) or quadrature phase shift keying (QPSK). And now let's focus on QAM, Quadrature Amplitude Modulation. Quadrature Amplitude Modulation, as the name suggests in Quadrature, uses two key parameters of sinusoidal wave, amplitude and phase, to encode information. By varying these two properties, Quadrature Amplitude Modulation achieves a two-dimensional representation of data. Each unique combination of amplitude and phase corresponds to a specific binary pattern, enabling the transmission of multiple bits per symbol. In 16 QAM, for example, there are 16 distinct combinations of amplitude and phase, allowing 4 bits to be transmitted per symbol. In 64 QAM, there are 64 combinations, allowing 6 bits per symbol. And in 256 QAM, introduced in LTE Advanced, 8 bits can be transmitted per symbol. The higher the QAM level here, the more data can be transmitted per symbol. However, higher levels of QAM require better signal quality because they are more susceptible to noise and interference. Now let's break down the mechanics of quadrature amplitude modulation. So imagine Cartesian coordinate system where the horizontal axis represents the I component, which is in phase, and the vertical axis represents the Q component, which is quadrature phase. Each point on this grid, called a constellation point, represents a unique combination of amplitude and phase. Now here's how it works here. So the amplitude variation, the distance of the point from the origin, determines the amplitude of the signal, and the phase shift, the angle of the point relative to the horizontal axis, indicates the phase shift. And together, these two dimensions encode a specific binary pattern. For example, a point at +1, +1 might represent the binary sequence 1101, and a point at -1, +1 could represent 0000. These are just examples. So the result is a compact and efficient way to transmit data. And from a mathematical perspective here, quadrature amplitude modulation signals can be expressed as a combination of two sinusoidal waves. So you will have the in-phase component, which is horizontal axis, quadrature component, which is vertical axis, and carrier frequency. Now, the sinusoidal waves are orthogonal, meaning they don't interfere with each other, allowing independent modulation of the I and Q components. This orthogonality is a key reason why QAM is so effective. In LTE, QAM is used on each subcarrier within the OFDM framework. So if you forgot about what OFDM is, you can watch the previous lecture. And depending on the signal to noise ratio here, S on R, LTE dynamically adjusts the modulation scheme. So we have the QPS key, quadrature phase shifting keying, used in poor signal conditions, transmits 2 bits per symbol. 16 QAM, used in modern signal conditions, transmits 4 bits per symbol. 64 QAM, used in good signal conditions, transmits 6 bits per symbol. And 256 QAM, introduced in LTE Advanced, used in excellent conditions, to transmit 8 bits per symbol. And this adaptability ensures efficient use of available spectrum while maintaining robust connections. On the receiving end, the QAM signal is demodulated to extract the original data. This involves separating the I and Q components. Using mathematical operations, the receiver extracts the in-phase and quadrature signals. Mapping constellation points. The extracted signals are matched to the nearest constellation point on the diagram. Decoding the bits. Each constellation point corresponds to a specific binary sequence, which is decoded to recover the transmitted data. The accuracy of this process depends on the signal quality. High noise levels can cause errors as the receiver signal might deviate from its intended constellation point. While QAM is highly efficient, it's not without challenges. Noise sensitivity. Higher order QAM schemes like 256 QAM are more sensitive to noise and interference, making them suitable only for high SNR environments. Implementation complexity. Generating and demodulating QAM signals requires precise hardware and software. Power requirements. High-order QAM schemes demand more power, which can be a concern for mobile devices. The QAM isn't just a theoretical, it is at the heart of many everyday technologies. Mobile networks, for example, LTE and 5G use QAM to deliver high-speed internet. Wi-Fi. Modern Wi-Fi standards like 802.11ac and 802.11ax rely on QAM for efficient data transmission. These applications highlight QAM's versatility and importance in modern communication. While this lecture focuses on LTE, it is worth noting that 5G, which you will learn in next lecture, takes QAM to the next level. So with the support of 1024 QAM, 5G can transmit 10 bits per symbol, further enhancing data rate. However, this requires even better signal quality and advanced error correction techniques. Now, to summarize, Quadrature amplitude modulation is a powerful and versatile technique that enables efficient data transmission by encoding information in both amplitude and phase. Its adaptability makes it ideal for LTE, ensuring reliable and high-speed connections in a wide range of conditions. In the next part of this lecture, we will explore how these modulated signals are organized into resource blocks, frames, and slots in LTE. Stay tuned and thank you for joining this deep dive into QAM. I'm Typhoon and I'm waiting you in the next lecture. Hello everyone, I'm Typhoon and welcome to another in-depth lecture on LTE technology. Today we are focusing on TD-LTE, time division LTE, a variant of LTE's air interface that operates differently from the widely deployed FDD-LTE, which is frequency division LTE. While the frequency division LTE dominates most LTE deployments globally, TD-LTE, time division LTE, has carved out its niche in countries like China and United States and parts of Europe. In this lecture, we will explore how time division LTE works, its unique features, and its advantages and challenges. Now let's start with a quick comparison here. Unlike the FDD LTE, which is frequency division LTE, which uses two separate channels for uplink and downlink, the TD LTE operates on a single channel for both directions. This approach comes with its own set of advantages and limitations, which we will dive into shortly. Now, since TD-LTE uses the same channel for both uplink and downlink, it requires guard period to avoid interference when switching between transmissions and reception. This guard period accounts for transceiver switching time and timing advance. Transceiver switching time, the time it takes for the device to switch between the uplink and downlink nodes, and by the timing advance, I mean devices farther from the base station must transmit earlier to ensure their signals align with those from closer devices. This factor influences the length of the guard period. Time division LTE supports two switching intervals, which is 5 milliseconds interval, which is also 5 subframes, and 10 milliseconds intervals, which is 10 subframes. Each interval includes a guard period, ensuring smooth transitions while maintaining synchronization. TD-LTE provides flexibility through the various TDD configurations, which dictate how subframes are allocated to uplink and downlink. For example, the configuration assigns 6 subframes for downlink and 2 subframes for uplink, 2 special subframes divided into downlink, guard period, and uplink portions. So this asymmetry reflects real-world traffic patterns where downlink demand often exceeds uplink requirements. However, this imbalance can limit uplink capacity, which is a key consideration in network planning. System information in TD-LTE. Time division LTE carries broadcast configuration details in system information block 1, and key parameters include subframe assignment, which defines the ratio of downlink to uplink subframes, and special subframe patterns, which specifies a division of special subframes into downlink, guard, and uplink slots. But we also have some challenges in time division LTE. One of its uplink capacity. A major limitation of TD-LTE, time division LTE, is its reduced uplink capacity. For example, in a 20 MHz carrier, TD-LTE dedicates only 20% of resources to uplink, yielding theoretical speeds of like 15 megabits per second. If TD-LTE with a separate uplink and downlink channels offers up to 75 megabits per second in the uplink direction. So this difference impacts applications requiring substantial uplink bandwidth, such as a live video streaming. We also have some complications with hybrid automatic repeat request mechanisms in TD-LTE, face unique challenges due to asymmetric subframe allocations. Some subframes must carry negative acknowledgement feedback for multiple transmissions, adding complexity to the process. Efficient scheduling is the backbone of LTE's performance. Unlike decentralized systems like Wi-Fi, LTE relies on network controller scheduling managed by the eNode B, which you learned in previous lectures. So this centralized approach offers several benefits here, I will count the 3 here, which is reacting to changing radio conditions in real time, ensuring quality of service for different users, and managing overload situations effectively. Now, let's break down how scheduling works in the downlink and uplink directions. In the downlink, the eNode B scheduler handles all incoming data from the network, deciding how to allocate resources to users. Now, here's how it works. Dynamic scheduling is ideal for bursty traffic like web browsing and video streaming. The scheduler's decisions are influenced by QoS, quality of service requirements, and radio conditions, prioritizing bearers with specific bandwidth and latency needs such as VoLTE, and balancing resource allocations to maximize overall cell efficiency while ensuring fairness. The scheduling process involves 3 steps: determining the number of users to schedule in a subframe, allocating resource blocks to each user, and broadcasting control information via the physical control format indicator channel. And for applications like voice calls, which generate low bandwidth, periodic traffic, semi-persistent scheduling is used. Instead of assigning resources dynamically for each transmission, a predefined pattern reduces overhead, improving efficiency. In the uplink, the scheduling ensures efficient use of the physical uplink shared channels, and here's how it works. First, it is requesting resources. So if new resources are assigned, the mobile device sends a bandwidth request with a physical uplink control channel or during random access. And active devices include buffer status reports in their transmission, helping the eNode B allocate resources dynamically. And we also have the second step, which is granting resources. So uplink scheduling grants is sent via the PDCCH messages, and the eNode B considers factors like the device's power headroom to determine appropriate modulation and key coding schemes. The key advantages of LTE scheduling include but not limited to real-time adaptation. So the eNode B continuously monitors radio conditions, adjusting allocations to optimize throughput and fairness. Efficient resource utilization. By considering factors like signal strength and quality of service, the scheduler maximizes the overall capacity of the cell. Power efficiency. Features like discontinuous reception (DRX) reduce device power consumption by limiting unnecessary monitoring of control channels. In this lecture, we have explored the intricacies of TD-LTE and LTE scheduling, from the unique characteristics of the TD-LTE, time division LTE's time division approach, to the dynamic and semi-persistent scheduling techniques in LTE. These features highlight the adaptability and efficiency of modern mobile networks. In the next session, we will delve deeper into key mechanisms to explore how LTE ensures reliable communication despite the challenges of wireless environments. Thank you for joining and see you next time. Welcome back, and in this lecture we will delve into the fundamental procedures that make LTE communication possible. These include the essential steps a mobile device takes to connect to the network, synchronize with a cell, and activate its data bearers. Understanding these procedures is crucial for appreciating the complexity and efficiency of LTE technology. We will also touch upon advanced topics like resource scheduling and efficient data transmission. Let's get started by exploring how a mobile device identifies and connects to an LTE cell. The LTE air interface includes several key procedures that govern communication between a mobile device and the network. These procedures utilize the reference signals, control channels, and shared data channels discussed in earlier lectures. The major steps include cell search and synchronization, attach and default bearer activation, and resource scheduling. Each step builds on the previous, ensuring seamless communication. Now let's look at these procedures in detail. Cell search. When a mobile device powers on, its first task is to locate a suitable LTE network. This process involves guided search using SIM information. Modern SIM cards contain the home public land mobile network with access technology field. This is a long field here. This field tells the device which radio access technology like GSM, UMTS, LTE to prioritize. So updated SIM cards guide the device to search for LTE networks first, optimizing connection time. Leveraging previous cell information. Devices store the last used cell parameters before powering off. If the device hasn't moved significantly, it can quickly reconnect to the last known center, speeding up the search process. Full band and channel search. If the previous cell is unavailable, the device performs a comprehensive search across all supported frequency bands to locate synchronization signals. There are two types of synchronization signals: primary synchronization signal and secondary synchronization signal. Primary synchronization signal broadcasts every 5 milliseconds. This signal helps the device lock onto a potential cell, and secondary synchronization signal alternates every frame to allow frame synchronization and help the device determine the start of a frame. The synchronization signals like PSS and SSS, PSS means primary synchronization signal and SSS means secondary synchronization signal, occupy only the inner like 1.25 megahertz of the channel, simplifying signal detection. And once the synchronization is achieved, the device reads the master information block MIB from the physical broadcast channel PBCH to discover channel bandwidth, HR key configuration, and system frame number SFN. Now we can also read the system information, as you know, after obtaining the MIB. The device decodes system information block 1, SIB1, which contains mobile country code and mobile network code, NAS cell identifier, tracking area code TAC, cell barring status, and scheduling information for additional SIBs, system information blocks. And with this information, the device can determine whether the cell belongs to its home network and decide if it should proceed with registration. Once a suitable cell is identified, the device begins to attach procedure to establish communication with the network. Now here's how it works. Initial connection establishment. First we have the random access request. The device sends a connection request on the random access channel RACH to obtain initial uplink resources. Then we have the RRC connection setup. The network assigns a cell radio network temporary identifier and configures a device for signaling using signaling radio bearer 1. And lastly, we have the attach request. The device sends an attach request, which includes a temporary identity, GUTI, or IMSI, to the mobility management entity. Mutual authentication and security. So mutual authentication ensures that both the device and networks verify each other's identities. At this phase, we have integrity checking and encryption are activated to secure signaling and data transmission. Then we have session creation. The MME coordinates with the serving gateway SGW and packet data network gateway PGW to establish a data session. The PGW assigns an IP address to the device, enabling internet connectivity. And we also have the default bearer activation. A default bearer is established for basic internet access. This bearer uses a predefined quality of service profile and is configured by the eNodeB through an RRC connection reconfiguration message. And at this stage here, the device is fully connected and ready to exchange data. Efficient scheduling ensures optimal use of network resources. Now let's revisit how this works for both downlink and uplink communications. Downlink scheduling. The eNodeB dynamically allocates resources based on quality of service requirements like VoLTE and radio conditions, which is, we can also say that the signal strength. The scheduling process involves allocating resource block for each user and broadcasting assignments via the physical downlink control channel. And when it comes to uplink scheduling, in uplink scheduling, devices request uplink resources through bandwidth request on physical uplink controller channel and buffer status reports included in uplink transmissions. And the eNodeB assigns resources dynamically considering device power headroom and channel conditions. And when it comes to semi-persistent scheduling, like for periodic low bandwidth applications like voice calls, semi-persistent scheduling reduces overhead by pre-allocating resources for recurring transmissions. In this lecture, we have explored the critical procedures that enable LTE communication from initial cell search to resource scheduling. These processes highlight the sophistication of LTE technology and its ability to adapt to varying network conditions. In the next lecture, we will delve deeper into advanced topics like handover procedures and network optimizations. Stay tuned and thank you for joining this deep dive into the LTE. I'm Typhoon and I'm waiting you in the next lecture.